Okay, cool. So I hope everyone's here by now. Uh, I'll be starting the lecture. So let me just figure out how I get the whiteboard on screen. Yeah, I think it's over this. And yeah, I think that worked. I think everyone has the whiteboard now. I just need to disable other people being able to draw as well because I mean that would probably not be that great if I didn't disable that. Yeah, I mean other people can draw right now. So need to just really quick find the setting to disable that. Hmm. Okay, I'm like not sure how I disable that, so we're just gonna hope that. Okay, go into the person icon at the top right corner. Oh, okay, okay. Thank you so much. Yeah, that I think that works. Yeah. Okay, cool. All right, and I can still draw, right? Yeah, perfect. Okay. So, in this lecture, as I already said on Discord, we are going to be covering a bunch of different things. So to begin with, I'll be covering some built-in data structures you can use in C++. Okay, so this includes stuff like maps, vectors, all of that stuff. Even though this was already covered in a previous lecture, I think Samik covered it a bit, but I'm just gonna cover it just again for recap and for completeness sake. Uh, I'll be covering that. I'll be covering UFDS, Union Find Data Structure. Very popular, right? I'll be covering that, and I'll be covering amortized analysis. So all three very interesting topics, and like I mentioned before, in these topics actually tie together really well. By that, what I mean is that while studying amortized analysis, you'll see that actually UFDS uses amortized analysis, and we're going to be covering two pointers today, which also sliding window technique, same thing. That also uses amortized analysis, right? So I'm gonna start off with the most basic. We're gonna start off with C++ data structures. I hope everyone can everyone's aware of what we're gonna be doing today. And to begin, I would request everyone to like follow me on the whiteboard. So I'm just gonna write data structures over here. I'm just gonna write it. Uh, actually, yeah, I'll just write DS because I have to use my trackpad this lecture. Okay. So if everyone can see the DS written on screen, please confirm with a yes in the chat. Otherwise, try to find where the DS is written because I will be doing all of the other stuff. Okay, great. So a lot of people can see. That's perfect. For everyone who cannot see, either follow me on the whiteboard or just like manually find it. That's where I'll be. If I'm gonna write stuff, I'm gonna basically write it here. Okay. So, uh, in this lecture, I will be covering the actual data structures, but I may not go too much into depth on how you implement them yourselves because I think that's gonna be a bit out of scope. Okay. Okay, so cool. I'll begin now. As you may know already, a lot of languages come with this thing called a standard library, right? I mean, every single language, even like the lowest level, something like C, even that comes with like its own standard library. So it's kind of true for every language. You know, it comes with a standard library that allows you to do stuff with it. So just as an example, you wouldn't even be able to take an input in C++ without a standard library. So a standard library is actually. Okay, wait, hold on. I don't know why, but my view keeps shifting because I keep following people. I don't know how to disable that. Okay, wait. If I press follow my view, okay, does that fix it? Okay, anyway, so besides that, like I was saying, you wouldn't be able to take an input without the C++ standard library. So it's pretty obvious that the standard library is very important. So like the IOStream header file, I'll have to write it unfortunately. The IOStream, this header file itself is a part of the C++ STL. The first data structure we'll be covering, any guesses? I mean, I don't know if you guys would even guess this actually, because I don't know how many people would even classify it as a data structure. But I want to see what people think. So, yeah, vector, yeah, exactly. So we're going to be covering std vector as our first example. So, I mean, how do I draw these colons better? I think this is the only way. Okay, I think this is really acceptable. And vector, yeah. So std vector. How many people over here already know what it is? I hope we have at least 5-6 people who know what a vector is. Okay, so 1, 2, 3, 4, 5. Okay, yeah, perfect. That just makes it even better. So then I can go through this part a bit faster, but I will still cover it. So for the people who don't know it, don't worry, because I'm still gonna cover it. I will temporarily share my screen and stop sharing the whiteboard. Okay, because now I need to show you guys code. Okay, cool. So I hope that you guys can see my screen. I've switched to VS Code. I hope you guys can see that as well. I'll make the font size a bit bigger. Yeah. Can everyone see VS Code? I hope we have some yeses. Okay, great. Uh, I think I should maybe pop out this window as well so I can see the chat. But I don't know if I can do that or not. I think it's fine. I'll just switch back eventually. Okay, so this is the first example of vector that I've come up with. So I'm just gonna let you guys take it in firstly. We made a vector a over here. It's vector int of a, right? Then we have used this function, which I haven't told you what it does yet, but we have used it, and then we have printed a.back, and that ends up printing 2. I can actually, why am I just telling this to you guys? I can like compile the code and show you the exact output. Oh, that's not the right thing to do. Okay, so I will compile vector1.cpp. Let's run it. Okay, so we get 2523, right? So the first 2 is printing this thing. That's the 2. Then we are pushing back 3, and now we are printing a0 plus a1. That's giving me 5. We're printing a.size. That's giving me 2. We're swapping something. We're printing, removing the back element. We're printing this again. So you guys will mostly be like, what the hell is going on, right? Either you know vectors and you know everything what's going on, or you don't know vectors and you like have absolutely no clue what's going on. There's 2 boats you can be in basically. So I believe in like, first showing the code and then explaining. So that's why I showed this code first. Okay, so now I'll go back. Now I'll go to actually explaining it. So vector is actually just a dynamic array. Okay, so you can think of it as an array where you can add elements and you can remove elements, and you can actually do all of that in O of 1 time. So by the looks of this code, can anyone guess? Let's just remove all of this for a second. Can anyone guess what pushback actually does? Just by the basis of this and by the fact that I told you what a dynamic array is, or that it is a dynamic array. Adds an element to the back. Yeah, exactly. So we have this vector which is actually empty right now, and when I call pushback, it becomes like this. And now extrapolating, what do you think dot back does over here? Dot back. I mean, okay, I pretty much showed the answer. I didn't mean to do that, but yeah. Just gives you back the last element. Exactly. Yeah. Now I'm pushing back 3. This makes the vector 2, 3, right? Now I again print a0 plus a1, and over here I get 2 plus 3. So I've taught you guys 2 things for like till now. A dot back gives you the last element, and you can also get the last element by, you can get any element. You can get the 0th element by doing a and then these brackets and then 0. You can get the next element by doing these brackets and then 1. Right? So 2 plus 3 gives you 5. Then what do you guys think A dot size does over here, this line? What do you guys think A dot size does? Length. Exactly. Yeah. This all very straightforward questions. Everyone's getting it right. That's great. So since there are two elements right now, it's going to print two. Now, what do you now? Actually, I haven't told you guys what swap does. Basically, if I have something like int a is equal to 2, b is equal to 3, and I do swap a b. Uh, Actually, I can't call this variable a because there's already a vector called a. If I do this, this basically makes it so a becomes 3 and b becomes 2. That's all swap does. So now when I do swap over here, that makes our vector equal to 3, 2. And now I remove the last element. So that's what popback does. I remove the last element. So you can think of it as pushback adds and popback removes. And now when we print the last element, it's again just gonna be 3. So how many people understood what's going on here? Or actually, let's ask how many people didn't understand. If you guys understood this, by the way, that's like that's pretty much vectors done, but I have included more examples because just for the sake of it, I've included more examples. Okay, that's vectors. So now we're gonna move on to the next example of vectors. So by the way, this popback method, it returns the last element. The way this is gonna work is I'm gonna show you guys more code examples. This one I explained, right? The next three, as you can see, there are three. I'm not going to explain them. I'm just gonna show you guys them, and then after that, at the end, I'm going to explain all of them. Okay? Popback only removes the element. It doesn't return anything. Yeah. See, it only removes the element. It doesn't actually return it. Okay. So let's do what I said now. I'm gonna go to the next three examples. So this is, I think I have comments in them though, or maybe I don't. Maybe I do, but yeah. I'll keep each one on screen for some amount of time and then I'll move to the next one. You know what? I think I can maybe like put two examples on the screen at once as well. I think that would be probably better. Yeah. Next example. And I think I can remove this one now. And this is the last example. Okay, so we check if people are okay. Yeah, as expected, there are quite a lot of questions. That's good. I'm just going to keep I'm just gonna keep the code on screen and I'll let everyone parse everything what's going on and after that I'll answer the questions. Till then, if you don't know what something means, I want you to just kind of guess what you think will happen or what the code is actually doing, and then after, because that's the point of this exercise. And after that, I will actually explain what is going on. Okay, I'll remove this example for now and I'll just put back the second one and the third one. I'll just put these two back on screen. Okay, so now I'm gonna start with explaining the first one. Is everyone okay with me starting to explain the first one? Or does anyone need more time to try to just understand what's going on with the first one? How much slower are vectors than arrays? Okay, so the thing is, it really depends on the question in hand, and the question is, the answer is that generally it really depends, but in like 90% of cases they are like equally as fast, and you won't see any measurable difference. Any measurable difference. But I'll get to one thing. What's a case where there is a measurable difference? So when there is a measurable difference, it generally comes down to when you're misusing vectors and somewhere you're not supposed to. And I can give examples of that at the end. Okay? Okay, perfect. So I see a lot of questions in chat, so I think now it's the perfect time to start by explaining this. Okay, so let's see. High level overview, what is this doing? This is declaring a vector of size n. Then it is doing some kind of mysterious for loop. I don't know what the hell this means. Saying for int I in A. For some reason there's an like an and sign here. Whatever that's supposed to do. And then it's taking an I. It's declaring another variable. That ampersand sign is there again. And we're doing sum plus equals I, and then we're printing the sum. Okay, so my guess is that this code takes in an array and it will output the sum. Let's actually see if that's what that does. So I'm gonna run it. Maybe I'll do 5, 1, 2, 3, 4, 5. Okay. And 1 plus 2 plus 3 plus 4 plus 5 is 15. So, okay, yeah, seems like that's what the code is doing, right? Now the next question is, why is it doing that? Okay, so I guess I understand this line. What does this ampersand mean though? Does anyone... I did start recording. Yeah, I'm pretty sure I'm recording. Yeah, I started recording. Yeah. Okay. Anyway, so my next question is to everyone here. What does this mean? What exactly is this for loop doing? Because I mean, maybe you guys have seen for loops. They kind of look like this, or like not even this. You've generally seen them look like this, right? So, what the hell even is this? Means constant for every I in some A reference variable iterating through each object in A. Okay, so there are parts of correct answers here. So what Ekant said is correct. You are iterating through each object, and what Chaitanya said is also correct. That it is a reference variable. It's actually combination of both of these here. Iterating through each reference object in A. So for every I in some A, yeah. I think someone asked this, and I was gonna ask it actually. Well, what happens if we change this to not reference? What exactly will happen? So before I tell you what happens, I think it's a better idea to just remove them and see what happens. So let's just try the same example again. Okay, so for some reason now it prints 0, which is very surprising because all I did is I removed like just 2 characters from the code. So what is exactly going on? I think I can clarify this best with an example. Let's remove this for now and just gonna do this. Okay, so now I'm entering 5 and it's printing 0. Okay, what does this suggest? This suggests that the default elements in the vector seem to be equal to 0, right, for int, because otherwise this could have been any bullshit value, but it actually turned out to be 0, right? So actually suggests that maybe the default value is 0 for everything. Okay, we can test out that theory as well. Let's actually see. Right, I mean that's the best way to figure stuff out. So I'm gonna use a simple for loop this time, and I'm just printing every element, right? Everyone understands what this for loop does, right? So what do you think this will output? Just as a wild question. Yeah, n zeros is correct. So the reason it's not all numbers input is because I actually never taken the numbers from the input. I actually removed that part. It will print n zeros, but again, let's test it out. Don't just take my word for it or people in chat. So I write 4, prints out 4 zeros. Right, so this is the first thing that I want to teach you guys about vectors. Okay, not the first thing. This is, let's say this is the next thing I want to teach you guys about vectors. When I write this over here, when I write vector a of n, this makes a vector of size n and sets every single element to the default value of int, and the default value of int is 0. That's why it prints 0. Okay, now actually if we go back here to our original code, which let me just do a bunch of undos, and I think we'll reach there. Yeah. Okay. Cool. So this is the original code. What I'm going to do is I'm going to remove the ampersands again. Uh, and now I'm going to look at what this printing was printing again. So we were actually getting 0 as the output, right? So this suggests that, oh, there's something wrong with this code, right? It looks like even after we do everything, the sum of everything is still coming as 0. Why is that happening? Do you guys get what I'm saying? Okay, hold on. I need to read what's written over here. I is the I is in I is in the out is the for loop. We can. Okay, I actually didn't really understand what this meant. It would be great if you could rephrase. Uh, what Advik
Actually,
said.
I was telling that the I variable is only declared in the for loop. We can only use in the for loop. So if we declare the I variable outside the loop, then we don't have to use the ampersand sign.
Hmm. Uh. Okay. Could you just repeat once? I still don't think I understood. You're saying we declared it outside the for loop.
Yeah, then we don't have to, I guess, use the ampersand.
Okay. Uh. That's a pretty good guess. I'm happy that you guys are actually trying to answer these yourself. That's actually very good. So you'll actually, I'm gonna tell you what it is in a second. But yeah, does anyone else wanna like try to guess? Okay, so Advik already knows what it is. So anyone other than Advik wanna try to guess what the thing does? Preferably anyone who doesn't actually know. So if you're like 100% sure you know it, then don't guess. If you feel like you don't know it, then I would like for you to try to guess what's happening. By the way, what Ayesha said is also correct. That is indeed the result, but my question was more of why it is happening. Okay, so by the way, the reason I'm spending so long on like this small thing is because it's actually like pretty important. It's less about vectors and more about like C++, but I think it's still important. Let me actually give you another example. I think once I show you this, you guys will all instantly understand what's going on. What is this code going to? Oh, sorry. What do you think this code is going to output? Yeah, it's gonna output 2. However, now I'm gonna make a small change. What do you think it's gonna output now? Actually, an interesting question now. Okay, so I haven't opened chat yet, but I'm assuming everyone's thought process is gonna be like, well, he said it output 2 before, and he said this is interesting. So it's definitely not gonna output 2, so maybe it's gonna output 3 because that's the only other number I see here. Uh and you would be right, it actually does output 3. And the reason it outputs 3 is because this ampersand sign means look at the exact element. That's what a reference means. B is referring to A. B is just another placeholder for A. And okay, so we actually had some people guessing 0, which is actually a fair guess because maybe from the previous example. Yeah, it's kind of like a symlink, yeah, almost. In Java, all objects are by default reference objects, yeah. Okay, so oh my god, actually I had a lot of people still thinking it's 2. Oh wow, okay, so that's nice. Okay, so now that means you guys actually learned something. That's great. So as you can see, it's not 2, right? Yeah. What Advik said is exactly right. They point to the same thing. So this thing means that B is like just another thing for A. B is just another, like, let's say I wanted to make another copy of a variable, but I wanted to call it something else just because say the original variable name was very long or something, and I wanted to make a short name for it. Then I would write like the ampersand sign for that. This is a feature of C++ called reference variables. And now that, okay, so now if you guys have accepted that this is gonna output this, I'm pretty sure everyone over here understands why adding an ampersand here is the difference between it actually changing the value and it not changing the value, right? And actually the thing is, I don't need an ampersand here because we are never mutating I, so it actually doesn't make a difference, but I'm just going to add it. Okay, so I hope everyone is clear on this now. If not, then please ask. Or does adding an in the input change the game? So adding an in the input basically makes this a reference variable. So if we saw in the previous example, it actually outputted 3 and not 2, right? So if we extend that over here, I'm saying, like, if we take that as like a given, like, I mean, we can't argue with what we actually saw, right? So if we see that that actually happened, then can we see that how this code would actually not do the same thing, and this code would do what we actually want? This code is like the ampersand in that previous case where we modified b and a didn't change at all, right? And this code, and the code with the ampersand is the code where we made b the reference and we modified b and somehow a still changed. So that's exactly what we want. Even if you guys didn't fully understand the mechanism, what I want you to take away is this doesn't actually touch the value in a. This is kind of like saying in b is equal to a. It's kind of like this. I'll actually give you a very good analogy. This is like saying this, okay? Then if we do sin of I, that's not gonna do anything. It's not gonna modify it because this is a new variable, right? What this loop does right now is equivalent to this. These two are the same. But if I add an ampersand here, that's the same thing as adding an ampersand here. Now you can see how this will actually take in the input. Now this is actually just equivalent to this, by the way, because like I said, it's just a, oh, sorry, not this, it's equivalent to this, because like we said before, this is just like a reference to this. So I could have replaced I with the actual thing it's a reference to and it would work the same, which is what I'm doing here. I think hopefully now it's a bit more clear. Would this be correct? So the reason this wouldn't be correct is because int I and a will become 0 0 0 0 0. It will iterate over all of the elements in a. It won't actually iterate over the index, which is what you need. Did you understand why this wouldn't work and why the conventional pattern works? Okay, I see some people are still confused about the difference. Which is fine. I hope one thing. Okay, so can I explain vector to CPP once again? Yeah. So before that, I just want everyone to realize that this code over here, this is the conventional pattern you'll use. The ampersand is like pretty non-essential. I mean, sorry, not non-essential, non-replaceable. You have to have it, otherwise it won't give the correct output. And I showed you that with an example, right? If not anything else, at least everyone's understood that, right? Yeah, you can, but your code being shorter is actually pretty good, right? And actually, I'll show you some pretty nice use cases for this as well. Yeah, shorter is always better in this case. It doesn't decrease your time complexity, no. It's actually probably like identical code, but it is better in my opinion because yeah, in some other cases it does, like Advik said. Well, I can give you a case, but it's a bit out of scope right now and I have a lot to cover, so that's the only reason I'm not. But this ampersand I pattern is actually very good to keep in mind, and you guys should like just just keep it in mind, if not anything else, you know. That's all. And then as time passes, you guys will see, naturally understand what it's doing. But you know what, let's go to example 3. because now I think people who were confused before will probably become even more confused now. Like what the hell is going on, right? I mean, so any guesses as to what this code is doing? Not how it's doing it, but just what it's doing. What do you guys think this is doing? So I'll just put it on screen for a bit more time. Inputs A and B, setting pairs, or setting pairs inside a vector from input, taking A and B as inputs. So Lyra, if you mean by zero, if you mean dot first, and if by one you mean second, then you would be correct. Uh, what Advik gave is also equivalent to this, and that is what this code is doing. Yeah. Uh, Inputs n and then inputs A and B. So A and B over here is the dot first and the dot second of the pair. That's what. So in fact, the best way to teach this, I'll just show you the example that doesn't use mystical C++ features and does the same thing. I think that's probably the best way to do it. Yeah. So I'm saying that this code is the exact same thing as this code. Okay. And again, I'm not actually gonna tell you the exact pattern. I'm not gonna tell you the strict rules. All I'm gonna say is this is the same thing. And like for clarity, I can actually change this to X and Y because they're conflicting variable names. But the point is that they can conflict. That's another thing I want to show you guys. Okay. So now you can do with this what you will. All I suggest that you guys always use this first version because in contest time is money and you want to be able to code stuff as fast as you can, or let's say time is points, not money, because that's more relevant in the context of contests. Okay, so the point I'm trying to make is the auto keyword followed with this sign, the colon sign, and this ampersand keyword can do pretty cool things in C++. Time is lesser people solving the problem before you. Exactly. Anyone use data types in the for loop instead of auto? Is auto slower? Auto is not slower. People only use data types because sometimes it's more clear. That's why. Also, I think C++ 17 does support it. Less than C++17 does not. That's the thing. Okay, so I hope you guys are intrigued by auto now, and this ampersand and these interesting kind of for loops. If you guys thought that was it, I actually have another example, which is vector 4, which actually takes this even crazier. I mean, if you guys thought that was the final level, that was not the final level. Okay, but realistically speaking, this is probably like almost the final level, or you can't really go more than this. I mean, so for our purposes, this is the final level. So like always, I'm gonna ask you guys to guess what this code is doing at first, and I feel like most people will guess it right. And then more importantly, I want you guys to realize how I've used auto and stuff to just speed up my code, and where I'll place the ampersands and everything. In this case, no ampersand is optional. Every single one of them is needed for it to work properly. You know what I think what would be better is, can someone here send me a double for loop that does the same thing as this without using the colon? Yeah. Can someone here send me a double for loop that does the same thing without using a colon? I'm gonna stay on the screen for maybe like, I don't know, like half a minute, and then I'll go back to chat to check. Yep, both of the people who answered have correct answers. Yeah. All three of the people who answered have correct answers. Yeah, exactly. That's exactly what this does. And now you know a way to. Okay, so Akshay, you actually forgot the I, so your answer is almost correct. Um, but yeah, everyone else who answered got it right, which is perfect. So now you guys know how to write it in an even shorter way. And I would suggest that everyone use this way because again, like I said, time is money. Or sorry, not time is money. Time is points, and time is people. Time is the less people who solved the question before you, which is very important for flex value. Okay. Anyways, so one more thing you guys may have noticed is I'm making a vector of vectors, which is pretty crazy, and yeah, you can do this. So the thing inside these, like, I don't know, triangle braces, it can be something like vector of int. This is valid. You can also make it a vector of a vector of int. That is also valid. And what this is going to do is it's going to, so if I represent a vector as like 1, 2, 3, okay, then a vector of vectors will be like this, but like again, there could be like 4, 5, 6 here. So you can see that each and every sub element is a 1D vector itself. So this is what a vector of vectors is, and again, the point of this example is to show you that that is possible as well. Now I think one more question which I think one more question which maybe some people will have is why the hell would I use this over C style arrays? Yeah, you can do that too. That's also valid as well. So the point is that you can be crazy with this, basically. you can nest as much as you want. Yeah, C style arrays. So C style arrays are arrays like this. Um, this is what a C style array is. So why would I use this over C style arrays? And the answer is that C style arrays are very annoying to pass around. They kind of destroy your scope, and as you will see, for some things like DFS and graphs and stuff, they are very very inconvenient to use. And in almost every single place, like in IOI, they give you stubs where they use vectors instead of C style arrays. In almost every single place, you will see everyone using vectors. It's just a more modern option, and so I would suggest again everyone over here to use vectors too. Oh yeah, vector functions as well. Uh, that's actually a major thing. I don't know how I forgot mentioning that. You can use some STL libraries like from algorithm you have reverse or you have sort, which you can use on begin iterators. I mean, we can use on end iterators directly. So you can do stuff like this. If you're using if you're using vectors, you get a lot of stuff for free basically. Sort works on normal arrays too, but you can't reverse sort directly with normal arrays, for example. And even accumulate works with normal arrays, but you can't use it. You can't be flexible basically. Okay, so uh, believe it or not, that's basically your crash course on vectors that is done. Oh wait, people have questions. Okay, cool. 2D array will be sorted row wise. So that would actually come under like that would I would cover this in a lecture on explaining STL algorithms, but just in brief, it first compare rows. The way it would compare rows is it would compare it like in alphabetical order. So you have like 1, 2, and 2, 3, then 1, 2 would come first. And after that it would actually compare the actual elements. Oh yeah, no, it wouldn't compare that, it would just compare that. What is the grid function doing? The grid, it's not a function, it's a double vector. That's the point. So now just before I move on, I'm going to show you every single thing you can use in a vector. So there exists vector int a, and you can just pass in a number n. This will create a vector with default elements. I can also do this. Okay, this will create a vector with each element set to 1. I can show you guys how that looks. So, oh, wait, what? Oh, I forgot to take an n. That's my mistake. Yeah. So now you can see instead of 0, it's 1. And the reason it's 1 is because I put a 1 over here. What is grid n vector int m? Oh yeah, so I hope now you guys, I hope you can understand that now. Now can you see this constructor thing? I've written 1 over here instead of zeros, so the default value everywhere is now 1. Now if you look at this example, the default value for each of those inner vectors is a vector int of size m. Uh, I'll go back to this example just to clarify because that's a good question actually. I was gonna cover that only now. So look over here. Each element is a vector int. So over there we set the default value to 1. Over here we're setting it to this. And now the default value of this we already know is all of them are like zeros. You know, so this will make an n by m grid where everything is 0. It's just one of the ways to do it. Right, does that make sense, everyone? Can you please explain why in the first program a was printed as 3 instead of 2? This is exactly the correct explanation. This is pretty much exactly the explanation. When you say, oh wait, sorry. This is almost correct. It's not exactly correct. It so it is over here you're actually confusing two things. This would be true if you did this would be true if you did this. It's basically like your understanding is right, but your syntax is wrong. But that's fine. I'll just show you. It's written like this, where you put the ampersand over here. I know C++ is a bit weird, and in that case, you will print B, and it will be the same thing as A, and we can set B to 3, and A will also be equal to 2. Oh, sorry, A will be equal to 3, as you can see. What you are talking about is something I'm not gonna cover now because I think it will confuse a lot of people if I do cover it. Yeah, I am not going to I'm not going to cover pointers right now. Yeah, what Advik said over here. That's what it actually is. Yeah. Can you like print the grid since I don't really understand? Oh yeah, sure. I shall print the grid. I will I will write an example over here. So let's take a 2 by 3 grid. So it's actually just gonna echo whatever I write over here. Oh wait, I didn't print it. My bad. Okay. So I input 2 3 1 2 3 3 4 5, and it prints the exact same thing. So now did you guys understand? Or still a bit unclear? Yes, it is a nested vector. That's all it is. It's nothing complicated. That's literally exactly what it is. Yeah, I mean, see, that's the point. The point is that you can nest it how much ever you want. That's the only thing I was trying to say. It's a bit unintuitive to some people. That's why I took some time to explain it. I didn't just say it as like a thing. But these, yeah, you can get 70 arrays. In fact, I think there was a JOIC problem. I don't know if Samik is still in the meet. Is he? Oh, he is. That's pretty cool. Yeah, I think there was a JOIC problem where Samik had solved it using like a 6D vector or something like that, and he literally had to write the constructor like 6 times, which was pretty crazy. I don't know if he's there right now and can hear this, he can confirm. But even if he's not, I can confirm for him. He had once done that, so you can absolutely have 60 vectors, 70 vectors, all of that crazy stuff is possible. Okay, hold on. I think I'm having some issues with connectivity. Let me just see what's going on. Uh, hmm. Okay, I think you guys can hear me better now, right? But if I turn on my camera, does that mess it up? Uh, it seems like it's fine. Okay, perfect. So everyone can hear me properly again. Everything's working. Yeah, cool. And maybe just like, how do I like not see my screen share? Or you know what? It's fine. Now let's move on to the next thing. Uh, next thing we'll be covering is STD set. So I again have an extremely long example. I'll have to unfortunately zoom out a bit just to fit the whole thing. I hope it's still somewhat visible. Okay, so like we did before, I'm just going to put this on screen, and before I tell you guys anything, I'm just going to let you guys guess what the hell is going on. Didn't we already know this? What? I mean, maybe you knew it. I don't know if the other I don't know if the others already knew this. Oh, this is just a font ligature. Um, it's like you can install a specific kind of font. Let me just check that the recording is fine. Okay, the recording seems fine. Yeah. Anyway, like I said, this is a font ligature. It just makes your VS Code look nice. You can also just Google it and you'll be able to. Yeah, it's the same thing as that. I just like, so you can see it's the same thing, but my IDE just makes it look nice. Okay. Anyway, people over here, did you guys understand what the code was doing? I showed a lot of things, so I mean, if you guys, if I switched back to early to the chat, then approximately which line were you guys on? We understood almost covered in lecture two. Yeah, it was mostly covered in lecture two. Yeah. Okay, so then actually, yeah, you're right. So I should actually probably speed up a bit because I have so much more to cover. Sets in Python are different from C++. As far as I know, yeah, they are different. They are different from how they are in Python. So I actually don't know Python that well, so I'm not going to comment on how they are in Python. All I know is they're like hash sets, and you don't actually have some kind of binary search tree in Python. Okay, so Advik is asking for a TLDR, so I'll do exactly that because again, like I said, a lot of stuff to do. So dot contain. So a set is basically like a set in math. It's like you don't have unique elements. I mean, sorry, you don't have duplicate elements. So if you have like 1 1, that's actually the same thing as 1, and that's what C++ will represent it as. This next thing is that inserts over here are logarithmic time complexity. So the time complexity is O of log n. Dot contains is again O of log n. It checks if 2 is contained in the set or not. I guess the name is pretty self-explanatory. As this comment says, you need C++20. There's also a way to do it without C++20, which uses this. Dot erase over here removes 2 from the set. So now the set is empty again. The set is empty again. Then over here, st.find is an iterator. I won't go into what that is. All I'm going to tell you guys is you should not even worry about what it is. You should write auto it and let the compiler worry about what it exactly is. So st.find is going to be equal to st.begin or st.end. Like, of course, it can be equal to more things, but Like that's the things you need to know. What is st dot end? St dot end is like the end of the set. So if my set was 2, then st dot, let's actually make a bigger set. Let's say our set was 2 3 4. Then st dot begin corresponds to 2. Next st dot begin corresponds to 3, and next st dot begin corresponds to 4. By the way, the reason I'm rushing with this a bit is because it was already covered in lecture 2. Otherwise I would go a lot slower. So I hope this is fine still. Yeah, it is technically this, but you do not need to know that. You can just write auto and not worry about it really. It's not a name given to the iterator. It's just the type hack to not avoid having to type this ugly long type. Now st.end on the other hand is a thing that comes after the 4, so it's next of this. So it's next of this. Now the reason we are checking if it's not equal to st.end is because that will check if it's equal to like one of these, right? Which means it's actually in the set. Uh, if it is equal to st.end, that's the thing that by default dot find returns when it couldn't find it. Yeah. st.size prints how many elements are there currently. Then again, we are inserting 7 and 6. Now this is kind of, I think, where it differs from Python. I'm not too sure, but over here, the thing is that even though we're inserting 7 first, when I iterate over it, it's going to iterate over 6 first. And the reason it works like this is because a set implicitly maintains all of the elements in sorted order. Not in just any random order you insert them in. It maintains everything in sorted order. And again, as you can see, I've written insert 6 again, but this really won't do anything because we can't have duplicates. Over here, the size will print 3 not 4 because this next insert didn't do anything. Dot begin points to the first element, which we just said is the smallest element, right? So if I add a star over here, I can actually get the element back. So this is the syntax to find the smallest element. On the other hand, this is the syntax to find the largest element. R begin means like reverse begin, so it checks from the end. And we can use a similar kind of for loop we did before to iterate over it in order of sortedness. So in brief, that is what set is. I'm now just going to answer doubts because oh yeah, I'm going to share this code. Yes, I am going to share this code in an article on SPOI after the lecture. Let's see. Oh my god, my net is cooked. Oh no, that's not a good thing. Is the recording's working? Even the recording is a bit cooked, which is also not a good thing. Oh, it's uncooked? Oh, perfect. Okay, you guys are gonna have to bear with me because I literally have 30 Mbps internet. My parents did not really want to invest in the best internet, which is pretty unfortunate. Especially given that I'm taking lectures, but it's fine. It's fine, guys. Trust. Okay. Anyway, so any doubts you guys have with this code particularly or with set in general? Because if not, then I'm going to move on to the next thing. I have to go a bit fast, unfortunately. S dot contain the same thing as s dot find not equals s dot n. Yeah, it's virtually the exact same thing. Yeah, and I know, guys, it's very unfortunate. If anyone here could give me good internet, I would be very grateful. But yeah, it's the same thing. Dot contains, but yeah. Actually, yeah, I don't know. I'm streaming, right? You guys saw how much time that GIF took to load. Just another proof of my internet. Using hotspot is actually a bit risky because oh my god, thank you. Somebody actually asked this. Okay. So actually, even Samik didn't know this until like a week ago. S dot count is not O of log n. It is O of log n plus log of n times the count of the elements. If you're using a set, they are the same thing. If you're using a multi-set, then dot count can explode to O of n, or O of n log n actually. So you should actually, ideally speaking, only ever use count when you have a set. If you have a multi-set, please never use count, please. I have warned you. Okay, my job is over. I hope you understood what I'm saying, right, Sam? I didn't ever say why it's slower, but I didn't explain that. I just said that it is slower, and it's like time complexity wise slower, not just like in terms of constant. Yeah, count gives the number of occurrences and contains just gives boolean. Yeah, that's correct. That's correct. Exactly. Okay, cool. So if those are all of the doubts with set, you can use count as long as you're using set. They're the same thing. Okay, because in set the count is either 0 or 1, so it's actually the exact same thing. But in a multi-set, it's not the same thing. So there's no reason to feel bad about set. Does set maintain sorting using heaps? Okay. So as much as I hate to not cover it, I actually can't cover this because I don't know. I think Samik will probably kill me. Number one, and number two, I don't think I'll have time. But I'll tell you in brief that uses this thing called a binary search tree. Some implementations use this thing called AVL. It's a kind of binary search tree. As far as I know, the C++ STL uses this thing called red black tree. I'm not sure. I'm gonna try to finish it as soon as possible. Yeah, we'll try to finish it as soon as possible, but it may be a bit longer. Yeah. So it doesn't use heaps. It uses this thing called a binary search tree. But like I said, we don't need to know what it uses. Although it's very interesting if you want to know. But unfortunately, I won't be able to cover that all the way till like I don't know, like lecture 100,000 or something, because there's a lot of other stuff I need to cover. All right, now let's move on. Yeah, it's. I mean, okay, yeah, it's not super useful. It is useful. It's just not useful in the initial stages. I mean, if you're trying to solve some Chinese NOI problem where you need like a tree, then it's pretty useful. But other than that, no, it's not that useful. Yeah. Now the other things we have. What does this test.cpp contain? Okay, it doesn't really contain anything. Okay. So the other things we have are std stack, std deck, std queue, std priority queue, and std map. Now I know Samek already covered map in his lecture, so I'm just going to not cover this right now because of time. I am not sure if he covered decks, so maybe I'll cover it. Again, I'm not sure about stacks, so I'll cover it. And I'm not sure about queue and priority queue either. As far as I remember, he did cover it, but I'm still going to cover it. Before that, though, before that, we are going to solve a problem, which is this problem. No, it's not. It's not this problem. It's this problem. Yeah. So in fact, I mean, what am I? Who am I kidding? 90% of you guys have probably already solved it, but for those who haven't, please read. Yeah, I mean, bro, imagine spoiling solution. But yeah, for everyone who hasn't read it, anyone who hasn't read it or solved it, please solve the problem. Please read it because it uses sets which we just covered. At least a solution of it uses sets that we just covered. Okay, so I'm not gonna actually like. Okay, in fact, this is the solution. What Advik sent. You don't have to use sets. You can if you want to. It's just a problem where you can use sets. Again, due to time, not gonna cover these problems, but you guys should solve it definitely and read it. Uh, for now, I'm going to move on to covering stack really quickly. Okay, the way I'm going to cover it is with an example again. The way you declare a stack. Wait, hold on. Hope everything's working fine. Okay, yeah, it is working fine. My computer is just a bit slow. The way you declare a stack is with this. Now, what does a stack do? You can see the number of the operations we have. We have emplace, empty, pop, push range, size, swap, top. A lot of operations. We are not gonna really worry about a lot of these. I'm just gonna show you the ones that matter. I think this is correct. I think my VS Code is just being a bit weird. Yeah, okay, it is correct, yeah. So this prints out the last element on a stack. If I do st.push 3 over here, it's going to print out 3. Oh my god, that's very slow. Okay, there you go. It prints out 3. The way a stack works is we have something that's empty. When we add an element, we add it to the back. When we remove an element, we also remove it from the back. I think there's like a term for this. I think it's called first in, first out. I think it's called FIFO or first in, first out or something like that. Yeah, I think it's called. It is just vector but worse, yeah. But for the sake of completeness, I felt like I had to cover it. By the way, the codes you guys are sending for the CSCS problem are correct, yeah. Is it LIFO? Last in, first out. Okay, whatever it is. I mean, okay, it's basically you just add elements to the back and you remove elements from the back as well. That's what a stack is. So the top gives you the back element and st.pop removes the back element. Now if I do st.top again, it's gonna print the next element, which is gonna have to wait for my computer to actually approve running this. I don't know why it's taking so long. Okay, there you go. 3 and 2. Yeah. Right? So now when are we gonna use stack? The answer is you're kind of almost never gonna be using a stack. For all real purposes, you should always use a vector and never use a stack. Like you know, it's actually kind of ironic, but stacks are somehow even I don't know how this is even possible, but for some reason stacks are literally slower than vectors. The reason they're slower is because internally they use a deck which is heavier. But it's actually so freaking ironic, and this is why you should never use a stack and you should just use a vector. Yeah, it's pretty useless. No, I mean, if you think about it, it's maintaining strictly less information than a vector, right? So if anything, it should be faster. Because a vector can do more. It can find the first element, last element, a middle element, whatever the hell you want. A stack can only find the last. So really, you should think that it would be faster, but it's like it's slower. Yeah, you can't access middle elements with a stack, so I'm not gonna go much into depth on it. You know, actually, the only thing you should really go into depth for in stacks is not stack itself, but it's this thing called a monotonic stack. Uh, but this is more of a concept in CP rather than a data structure by itself. And it's also not the topic of this lecture, but actually I think there's an article on Yusuko Guide called Stacks, where they actually never fucking teach stacks, they just teach monotonic stacks. So if you guys are like looking at that, oh my god, the question, how did I forget this? There's a difference between emplace black and pushback, which you will never basically need to know because the compiler will optimize it for you. That's the short answer. The long answer is that I think it's best to show it an example like usual. Yeah. Now, as you can see, this prints 1, 2, 3, 4. So pushback is we need to make a pair and give it to this. And place back is we kind of don't make the pair. We just call the constructor for a pair, which is actually what we are doing here. but we don't even call the constructor. We're basically saying that, hey, just make it directly. I'm just telling you what you need to make it. In short, this is the difference between it. Uh, is Dijkstra with set or Dijkstra with priority queue faster? Um, I feel like priority queue would be faster because of Fibonacci heap and stuff like that. Although I don't know if we actually use or if so unlike the freaking set and sorry, unlike the stack and vector thing where stack is like entirely useless. Uh, on the other hand, with queues you actually have this thing called the Fibonacci heap, which is a very fast heap. Which it's the same complexity, but it's amortized log n and it's really fast. And I'm not sure, but I maybe that's what. So basically, the thing is the priority queues will strictly win. What about lazy removals? I'm not sure what you mean by lazy removals. And placeback creates the empty object. Uh, while with pushback you have to do that work yourself. Yeah, pretty much. It doesn't create, and it creates a full object. It creates the object with what you tell it. But yeah, pretty much yeah. Off topic, but did you give ZIO? I did not give ZIO. I've actually not given ZIO like ever. Remove worst states from the set. I'm not sure if that would be faster because I haven't actually coded it. Um, I haven't ever tried it, so I don't know. Define pushback and place black. Please don't do that. That does not make any difference whatsoever, and it's kind of weird. Please don't do that. Okay, that's just so I've covered stack, the most useless thing. Now we are going to cover deck. So now decks are actually, you should never use them over vectors when you can prevent it, but they are actually useful. Okay, so a deck exposes. Let's again do this. Wow, a lot of methods. This is so complicated, right? The only ones we care about, we can see some familiar ones like emplace back. Oh, but there's an emplace front as well. That's interesting. Uh, pop back, pop front, push back, push front. So let's actually look at this. So I've seen that there's a method called push front. So let's try using it and let's see what we get. Can you guys try to guess what this is doing? I mean, I haven't explained anything. All I did is I looked at the methods using IntelliSense, and then I just wrote some random code, and seems like it's printing 1, 2, or it's printing 1 and 2. So let's make it more interesting. Let's do pushback 3 and push front 4, and let's see what it outputs now. Okay, it's outputting this. Okay. So now my question is, what do you guys think? So pushback, I'm pretty sure everyone over here can kind of guess what it does, right? What do you guys think push front is doing? Yeah, yeah, that's very much it. Yeah, exactly. Everyone's clear about this, right? Another question is deck greater than Q and stack. Is deck greater than Q and stack? Uh, yes, because both Q and stack by default use a deck. And yes, a deck is basically exactly like a vector, except you can also add stuff to the back. Sorry, you can also add stuff to the front, which you couldn't do using a vector, and now you can. Yeah, exactly. It's very useful for this one algorithm. Yeah, you don't need queues and stack, but I mean like people actually do use queues. Uh, a queue is like kind of like, okay. So actually, can anyone guess what the full form of deck is? I don't know, like if anyone knows, because I actually didn't. That's what I thought as well. That this is what I thought for so long. Um, which is why I always used to pronounce it as DQ as well. It was pretty funny, but I was disheartened to know that the full form is actually this. It's called a double-ended queue. Yeah. um, I know, even I was really sad because it sounded so cool. Even and when I learned that the pronunciation was deck, like it sounded like the English word DECK. Even then, I was like, no, man, I've been pronouncing it the other way for so long. My heart is broken. But yeah, it's actually deck, and the full form is double-ended Q. So by the name itself, you guys know what it is now. It's a Q, but it's double-ended, not just one end. Okay, but the question is, what even is a Q? Because I actually covered deck before Q, which is pretty weird, right? Let's do the exact same thing that I've been doing so far. Sorry guys, that was my mom. She didn't know I was in a lecture. We're going to ignore that. Yeah. Okay. So I mean, all of these data structures are so similar to each other that I'm pretty sure everyone can guess what this does as well. Right? So, do people understand this code? Yeah. Now I'm going to do q dot push 3, uh, q dot push 4, q dot push 5. Okay. Uh, q dot front, q dot size. You know what? Just to speed up my thing a bit, because my compiler is being very slow, I'm just going to include the header files I need. Yeah. I think this will speed up compilation by a bit. I mean, it's still pretty slow, but yeah. Now there's a difference between this and stack. So in stack, when you pushed in more stuff, it printed the latest thing that pushed in. Over here, dot front is actually printing 2, right? So it's printing the first thing we pushed in. So this is actually how a queue works. So I mean, I don't really need to say much. All I need to say is, imagine you're standing in line to buy something at a store. The person who's added to the line first is going to be at the front of the line. Is going to be at the front of the line. And when we pop them from the line, that's like saying they got their thing, they bought their thing, and they left the line. And when we push more people into the line, they get added to the back of the line. So it kind of looks like this. Oops. 2, 3, 4, 5, 6. And when you're looking at front, you're looking over here. And when you remove from, you remove from here as well. And when you add over here. That's what a queue is. I hope this is clear to everyone. Yeah, it's exactly like a real life queue. That's why you don't even really need to learn this, right? Because it's like the same thing. Let's see. Wait, I think there was a question that I didn't answer. Why not use deck instead of vector? Decks are implemented using vectors under the hood. Okay, since Samak is saying that, I'll trust it. I am not sure. Like, I haven't either verified this in the positive or negative. But yeah, that actually seems like it would be the case, because makes sense. Is deck worse in terms of time? Deck is slower. Deck is slower than vector, yes. And that is exactly the reason stack is also slower than vector, because stacks are coded using decks. Which seems very weird, but I know. It's in deck implemented as double-ended linked list. I mean, this is a very unoptimized implementation of a deck. It's like pretty awful for yeah, and decks support random access as well, exactly. So I'm actually not sure exactly how deck is implemented. How, like, I could implement one myself, but I don't know how C++ does it. Uh, but before that, let me just see if there's anything else I'm missing. There's a map and unordered map, but Samik already covered that in his lecture. I'll say in short that a map is actually, you know what, Samik did cover maps, so I'm not gonna cover them. So we are done with the first part of the lecture. In that case, everything I wanted to cover is done. So you guys can say yay or something. I don't know. I can say yay because I'm the one giving the lecture. So good for me, I guess. Yeah. I mean that's fine. The interesting stuff kind of starts now actually, which is pretty unfortunate for the people. But that's fine. Uh, okay. So now I'm gonna stop sharing my screen and I am going to open a whiteboard. Mm, for some reason, my old whiteboard just went away, uh, which kind of sucks. But that's fine. I hadn't really written anything anyway, so that's cool. Yeah. Uh, and again, I need to not let participants edit. Probably not let them start activities and follow my view. Cool. Okay. So now we are going to. I'm going to ask a very interesting question. I don't think anyone would expect me to ask this question. The question I'm going to ask is, how do we implement a vector? Suppose I gave you the task of coding S3 vector. My question to everyone here is, how are we going to do this? Like, I mean, it's obvious that there is a way to code this, right? Okay, so the operations I want you to support are pushback, popback, dot size, and random access. All four of those as a starter. Like I said, this is actually an interesting question, right? I mean, at least I hope it's interesting to the other people over here because it actually makes you think, right? By implement, I mean that you can't use C++ STL. You can, but you just can't use vector from C++. You have to basically code what we actually do. Like you have to code your own custom vector. Arrays are allowed. Yes, arrays are allowed. My internet died. Can you repeat what you said in the last 30 seconds? So basically, I said that I'm going to ask everyone an interesting question. And the question was, how do you actually code a vector? So, not just what a vector does, but how you actually code it. Okay, I'll give you guys some time to think, don't worry. We have a response already though. You create a new array of a new size every time everything something is added. Hmm. That is actually that is a valid implementation actually. That would work. Uh okay, you know what? Let me add to my question. Create a vector. So maybe I'll write, let's go here. Let me write create a vector, and wait, is there like a text tool I can use? That would be very um that would be very nice for me, although I can't seem to find it, so I suppose I'm just gonna have to write it manually. Okay. uh and analyze the time complexity. Yeah, so that is my question. So you can't you can't use a vector to create a vector though, unfortunately that is not allowed. That would be a cyclic dependency. I want you to do it without using vector. And with your implementation, I want you to also give me a time complexity analysis. Well, you don't have to. It doesn't even have to be correct, really. But I want you to tell me like a rough idea of what the time complexity of each thing is. Okay, let's see. So Samik says int array n. Yeah, you can. That's what you use to create an array. Yeah, you can use this basically if you want to. Can reserve be used in array? Uh, you can't use reserve in an array because an array size can never change. Make arrays and merge them efficiently. Hmm. In C++, does it? I think it makes a new array every time you go from size 1, 2, 4, 8, 16. Is it possible to delete things? This is actually correct. I think I can't set it first. Yeah, this is correct. Uh, but like, why does it do this? What is the logic behind it? Like I said, I don't just want a solution. I want a rough analysis of the time complexity. So suppose you're implementing it like this. What is your time complexity going to be? It's actually a tricky question, right? If you think about it. I mean, it's like really weird because if you look at it, let's say we had an array of size 16. As soon as we hit size 16, actually, wait, before I get to this, I'll actually explain exactly what happens. I'll tell you my implementation, or it's not mine. I stole it from C++, but I'll just tell you what C++ does. So we're gonna start off with an array of size 1, okay? We're gonna fill it with an element. Now suppose now I say that, oh, I want the second element. I want to push back a new element right now. So what are we going to do? We are going to discard this array entirely and we're going to create another copy of the array with size 2. I'll maybe make it here only. And now I have two spots. So in the first spot I'm going to fill whatever I had from before, which is the 1. And now let's say the user wants to add a 3. So I'll put the new element they want to add over here. Okay. You have some ideas like dynamic CHT from static CHT. I'm actually uh not sure how that really works. But wait, are you talking about square root rebuilding or something? I'm not sure. But okay. This was another method along with square root. Interesting. Okay. So let's say now I added another thing. Let's say I added like a freaking a 2 after this. Or let's say I added a 7. Okay. Is the old array just being kept in memory, wasting memory, or is it deleted? It's deleted from existence. We copy it to a new place and we delete it from existence. So we do the same thing again. Let's say I wanted to add like a 7. So now I'm not going to make a size 3. I'm actually going to make a size 4. And now I'm going to be 137. And now, doesn't vector add double the number of elements, which makes it faster? Yeah, that's what I'm explaining right now. Now say I wanted to push back another element. The user says he wants to push back like 4 or like, I don't know, 15, or let's say 4. I'm going to add 4 and notice this time it was free, right? I didn't have to create a new vector. I didn't have to create a new array rather. Now suppose I'm adding another element again. What am I going to do? I am going to make a vector of size, or an array of size 8. Oops. My lines are not very good. Does this have any relevance to the fact that computers work in binary and binary increases in powers of 2? So there are like two answers. The first answer is yes, it's relevant because it ends up being very fast implementation wise for that reason. And the second answer is that even if computers worked in base 10 or base 17 or whatever, this would be equally as fast. So it is relevant, but not in the way you expected, maybe. Okay. So 1, 2, 3, 4. This is 1, 2, 3, 4, 5, 6, 7, and is this 8 slots? 1, 2, 3, 4, 5, 6, 7. Yeah, it's 8 slots. Yeah, okay. So now this is gonna be 1, 3, 7, 4, and whatever element I said, 15. Oh my god, someone already has an implementation. Oh my god. Uh, New vector data size cap. Yeah, this looks like the right idea that we're talking about right now. Yeah. Okay, so Sam has an idea for a persistent segment tree. O of log n insertion on back and front, O of log n deletion, O of log n random access. Yeah, this is actually correct for integral data types. But do you see why this would not work if I had a custom struct? Right? Because now you can't really do anything. Yes, but I'm really happy that you came up with that, because actually you need vector to implement PST. No, you can do it with pointers. That's fine, right? I think you can do it with pointers, so that's actually fine. Uh, but but yeah, I'm actually really happy you came up with this, uh because you can actually use this idea in some problems where you need like a fast multi-set or something. So you can actually use a segment tree instead of an Oroch set in like a lot of CSCS problems, and this kind of line of thinking will basically help you solve all of them very trivially. So, anyways, so regardless of that, did everyone understand what I'm doing? I'm not asking about whether you understood why it's correct, wrong, whatever, fast, slow. Did everyone understand what I'm doing? What I wrote on board right now. So it's at size 1, then size 2, then size 4, then size 8, blah blah blah. Yep. Now my next question is, what is the time complexity of this? Advik, I am getting to that, by the way. That's a pretty good question, right? But I mean, okay, so how does it seem to be log n is also a question. So firstly, it's isn't it like super weird to analyze the time complexity, because in some cases we just don't do anything and it's like truly over fun, right? But in some cases we actually extend the entire vector and copy the entire thing, and in those cases, like, what is it? In those cases, it's O of n, right? Isn't that like so weird, you know? Like, how am I even gonna say a time complexity? So my first guess would be that, oh, this seems to be O of n because we take the worst case, so it would be O of n into n, which is O of n square. This would be my first guess. Because, I mean, maybe some people guess this as well. Is copying O of 1? So copying one element is O of 1. Copying n elements is O of n. So this would be my first guess, right? It turns out that this is like absolutely wrong, because I mean, if that was really the case, then vectors would suck. So it is not O of n. And why is it not O of n? I mean, let's think about it. Why is it not O of n? If we insert, let's say, like 100 elements, what is it? It looks like we're only really doubling the size. We're only doing that O of n worst case for how many of them? We're only doing it for like we're doing it for the second element we insert. Not yeah, we're doing it on the second element we insert, for the third element we insert, for the fifth element we insert, then we would end up doing it for the ninth element we insert. So it's always like a power of 2 plus 1, right? And everyone knows that there are only log 2 of n powers of 2 between 1 and 100, right? So we're actually only gonna do it like 6 to 7 times. Yeah, exactly. So that kind of hints towards it being like, oh my god, you know, maybe this is not actually so bad. So if we now do an analysis, we'll see that there are log 2 of n times that we are doing this copy, you know, and each copy moves n elements, so maybe the time complexity is O of n log n, right? Which is already really good. This is so good, right? We just went from n squared to n log n. So actually, yeah, you're right. This is not even n log n. It's actually even better than n log n. So surprisingly, uh, even this is wrong. Even this is wrong. And you know, every time someone sees it for the first time, they think it's O of n log n. I mean, actually, you know what? Even I thought it's n log n. Even I thought it's n log n, because I mean, it just made sense, right? By the way, uh, I don't think I ever said this, but I think people may have figured it out by now. I've started talking about amortized analysis, which is also something I was going to be covering in my lecture. This is amortized analysis, and I thought the perfect example is to take a vector. because it's like it's interesting, number one, and number two, it's such a good example where people make mistakes because it's like very non-trivial, amortized, and also the idea is just really genius in my opinion. I feel like this idea could be applicable in like so many more places, that I just really wanted to cover how a vector is actually implemented. So let's see, which color should I use for? I can use red maybe, or we can use blue. Amortized analysis, and I can draw a box around this. Okay, yeah. So this is amortized analysis. What did we do in amortized analysis? Can anyone think about what we actually did? Like, we thought it was n square, right? At first, because we were like, it's sometimes O of 1, sometimes O of n. So let's just take the worst case because that's what we do in time complexity. So it's like n square. But then I did something very interesting that made me conclude that this is actually like it's actually at least n log n. It's like it's n log n. I mean, it's actually better than n log n, but we concluded that it's better than n square and it's n log n. So can anyone try to generalize what we actually did? Uh, we scaled the number of objects to a higher number. That's what we did here, yeah. But I'm not talking about what we did in the implementation. I'm talking about how we analyzed the implementation. I'm talking about the change in how we calculated the time complexity. Motivation session for ZIO failures to grind ZCO. I mean, ZCO is a lot easier. I hope that's pretty motivational. Samek can also agree that ZCO is a lot easier. Oh, he's gone. That's very sad. I'm going to scold him after the lecture now. Trust. Okay. Anyway, uh, it is easier, and for the people who did qualify ZIO, you can give ZCO without any stress, and that's actually really great. For the people who didn't, don't worry because for the people who didn't, don't worry because ZCO is a lot easier. So anyway, let's actually get back to the topic in hand. Uh, anyone trying to answer? Because oh my god.
This meeting is being recorded.
Hello. I'm sorry. I think I accidentally pressed the back button and left the meeting. It's not my network. I just pressed the back button by mistake. It's just me being weird. Anyway, please tell me it saved my whiteboard. Please tell me it. Oh my god. Okay, so unfortunately, I don't think it saved my whiteboard, which really sucks. Uh, but what do I do? Like, do I just like I'll just write the n log n part again, and yeah, the recording is there, but the whiteboard itself isn't. So I'll just write this part again, and I remember I'd drawn my blue box and stuff is gone though, which is pretty unfortunate. Uh, I'll just draw across over here. Let's just continue from here. Okay. Oh wait, I actually need to draw the vector as well. So I will draw the vector as well. Apologies for that, guys. Okay, but anyway, my question still stands. No one has answered it yet. I don't think. What is the thing we did that was different from what we generally do while analyzing time complexity that allowed us to conclude that this is at least n log n? Max a into len a much bigger than sum a as I can phrase it. Okay, what is a in this case? The vector? I don't think we actually care about the actual number in the vector, right? So what does max a mean then? time per operation stored in A. Hmm. Hmm. So, hmm. So, Ekansh actually answered a different question. I was not. I was actually asking. By the way, Advik, your intuition is pretty much correct. Yeah. In this case, like the amount of times we do the burst operation is a lot worse than is a lot better than actually doing that burst operation every single time. So if I was to say it formally, what I was doing is instead of looking at the amount, instead of looking at the time complexity for one operation, instead of saying that the time complexity for one operation, so for one operation is O of some function of n. Instead of saying this, I was not doing this. What I was doing instead is I was saying that the sum over all operations, the time complexity is equal to some function. Do you get the change in mentality that we have? We don't actually care. We don't actually care about how much time each operation takes. We only care about how all of the operations together will take. Okay, so this is actually, I could end the amortized section here and I would have already explained everything. Like in terms of strictly what's required, this is what amortized analysis means. And if the sum of like this all operations is O of f of n, then we can say that the time complexity, the amortized time complexity per operation is O of f of n divided by the number of operations. This is what amortized analysis means. Amortized complexity is just accounting for the bad complexities that happen rarely. Yeah, I mean, yeah, kind of. And really speak, it's basically exactly what I said right now. Okay, so I see that Advik is getting pretty impatient, and he really wants to know why this is not n log n. Uh, so yeah, I'll explain that now. So we can actually the way we realize this is not n log n is actually I can't said it before. We're gonna add an element, right? 1, 2, 3, 4. Now this is when we are actually extended to this size. Over here, what we do is we copy all of these, right? The key is realizing you would maybe think that each element is copied log n times. That's how you arrive at O of n log n, right? Uh, Specifically to Advik, because I think he's the only one who even came up with the log n thing. Each element is copied log n times. What I want you to realize is that it is true that let's get a different color. It is true that this element is actually copied log n times. This element is copied log n times. But this element over here is actually not copied log n times. This is copied log n minus 1 times, right? Uh, this element is copied log n minus 2 times. This element is actually copied 0 times, because so you would think that, oh, this is so pedantic, man. How is this gonna really make a difference? And it actually turns out to shave off an entire log factor. So it pretty much does make a difference. And the cleanest way to see it is to realize not in terms of how many times each element is copied, but how many times we do total number of copies. Let's just look at that. So every single time we double the size, we copy the elements, right? And how many elements do we copy? We copy how many elements we have so far, which is not equal to n, by the way. So we copy one element when we are extending the size to 2. When we're extending the size to 3, we copy 2 elements. When we're extending the size to 3, we copy 4 elements. When we're extending the size to 8, we copy, when we extend the size to 16, we copy 8 elements. So this is actually equal to 2 to the power of, I think it's like 2 to the power of n plus 1 minus 1. Right? So you can actually just like hack this, because 1 plus 2 is 3, 3 plus 4 is 7, 7 plus 8 is 15. So you can always see it's like a power of 2 minus 1. You don't even need the formula. But yeah, you can use the formula and you'll arrive at the exact same result. So here we need to realize that n is actually log of n, right? Because the copying operation occurs log n times. So 2 to the power of log 2n plus 1 minus 1 is basically the same thing as what? It's the same thing as 2 into n minus 1. So this is equal to O of n. So I hope everyone over here, number one, understood. Some genius computer people, most definitely. Definitely not me. I couldn't come up with anything this insane. But yeah, I hope that everyone over here, number one, understood what's going on, understood what I'm explaining, and number two, appreciate how insanely cool this is, because in my opinion, it's like it's actually so cool. You'll see variations, like I said, of this idea. Uh, there's one variation that actually I can think of instantly, and it's that at every interval you rebuild, instead of rebuilding, instead of doubling the size. And that variation is used in this algorithm called square root decomposition. But really, in my opinion, it comes from the same like principle. That's why, which is again another reason I really wanted to teach this, and another reason I really like this idea. Yeah. Hmm. Okay. Now we're gonna take a detour to something else that we're gonna be covering in this lecture. So go ahead and read this problem, the one I was sent in chat. I won't be stopping my whiteboard because I will actually need it. Site can't be reached. Did I spell it wrong? Oh, I definitely spelled it wrong. Oh, it's not YP, it's JP. My bad. Uh, JP. There you go. Yeah. So go ahead and read this problem. Yes, I will be teaching UFDS now. The infamous data structure. It's actually a very nice data structure. I mean, you'll probably you'll probably like be reborn by reading how cool, or by learning about how cool this is. Okay, I mean it's not that great, but it's a pretty neat data structure. I think one of the most surprising things about this data structure is how easy it is to code. More than the theory even maybe. Actually, the theory kind of adds to the fact that it's so surprising that it's so easy to code. But yeah. Uh, let me know when everyone here has read the problem, so then I can begin by discussing it. Hmm. So I'll just read it myself. Like just to do it. You have an undirected graph n with 0 edges. You need to process the following q queries in order. The first query is add an edge u to v, and then the next query is if u and v are connected, print 1, otherwise print 0. So hopefully, okay, wait. I hope it didn't reset my whiteboard to begin with. Okay, it didn't. That's nice. Okay, anyway, so hopefully everyone's attended Man's lecture on graphs, or if you haven't, hopefully you know graphs. So we can obviously see that this is a graph theory problem, right? So the Yeah, so the regular solution now is that we make a graph, right? Whenever we're adding an edge, we add an edge. That's fine. That's all fun. And then whenever we want to check if U and V are connected, we start a DFS from U and we check if we have visited V after the DFS. So that's gonna be O of N, right? Like O of N worst case. So the total complexity of this is going to be O of N per case into O of Q into Q queries, which is O of N into Q. Hope everyone understood this solution. By connected, do we mean direct edge connection or connected by traversal? It always means connected by traversal because that's the definition of connected. Yeah, that's why the problem isn't super easy. Yeah. So everyone understands the DFS solution, right? Wait, do people have permission to draw? Oh my god. Oh, I just disabled it. Sorry about that. I don't think it's allowed anymore. Yeah, cool. Anyway, so what is N and Q? We didn't actually see that. Oh my god, N and Q are both 2 into 10 raised to 5. Okay, so this won't work for full solve, right? Fortunately for us, there is a data structure that actually solves this exact problem, and the data structure's name is union find. The union find data structure. So over here, union means you add an edge, and find means you find the component of an edge. Sorry, find the component of a vertex. So what does this data structure do? How we should think about this is how are we going to solve this problem? Okay. Now, what we can do is there's actually we can actually let's not even get into UFDS. I'm going to go to the adjacency list solution. I'm just going to go with that for now. Hmm. Hmm. Actually, you know what? Let me just draw it, and I think you guys will see what I mean. Okay. So we're gonna have nodes, multiple nodes. Everyone can see the 1, 2, 3, 4, 5, 6, 7 I'm drawing, right? By the way, I prefer DFS because it's just very easy to code, personally. So basically, what we are doing is, let's say we had to add an edge 2, 6, then we just draw a line like this, right? Then we need to add an edge 2, 5, so we draw a line like this. We need to add an edge 6, 7, so we draw a line like this. If we have to add an edge 2, or 5, 7, we draw a line like this. We need to add, let's say 2, 7, we draw a line like this, right? And then we just do a DFS, right? That's our solution. Now, there are two things to realize here. By the way, did everyone understand this solution at least? If not, then I'll need to explain it because I don't know if you'll understand the next part. If not, so please tell. Uh, what about the other people here? Has everyone understood it? Is there another way without DSU? Not that I know of. No, no. Pretty much, you don't really have a way without DSU. Okay, so I'm like 100% sure Advik has understood the question. So, uh, okay. Okay, I mean, I really would have expected more yeses. Uh, does this mean that like the other people haven't understood it? Okay, that's more yeses. Okay, that's pretty good now. Okay, cool. So now my first observation. I mean, the the only one who repeated their yes is I think Advik, but okay. The first observation is, suppose 2 and 7 are already connected, and I want to add an edge from 2 to 7. There's no point, right? We don't need to do that because they're already connected. Right? So this means that we're always actually going to have a tree, right? Does everyone see that as well? Or actually the technical term is a forest because it can be disconnected. So we're always going to have like multiple trees. It's never going to be like anything complicated. Not gonna have like a complicated graph. Right? Is anyone unclear about this? Like maybe like one doubt I can feel like maybe people will have is, what if we remove edges? Then it gets messed up, right? But the thing is, we never remove edges here. We're only adding edges. So we are never going to sacrifice any information, so as to say. If a program allows removing, then that is out of the scope of this lecture. We are not discussing a solution where we involve removing, because that's slightly harder than this. You'll have to use like a variation of this only, but it's like a lot harder than just solving this problem. So for now, we're only going to cover this problem. Okay, so that's the first observation. Now already we can see this allows for a bunch of interesting things. Firstly, do you see how we can just get rid of the adjacency list, and we can instead think about it as storing a parent for every single node? We can get rid of this, and we can just think about it as storing a parent for every single node. Right? This is just a direct direct thing of this observation. Now how do we, now in this new parent thing, if we think about it as a tree, basically, I'm just going to draw like a tree like this. Why can't we store pair int instead of adjacency list? Because then it will be pretty annoying to traverse and do like a quote unquote DFS on the graph to figure out if we are at the same thing or not. Okay, but anyway, so once we store this as a tree, how do we check if two nodes are in the same component? Well, we can just keep going up the tree from both of them, and we can see if we check the same root. If we reach the same root, right? That will mean they are connected. I'll actually use a different color. Does this idea make sense? Okay, that's good. So when I'm attaching a new node, I'm always pretty much going to either only attach it if it's like a new node, right? So if I'm attaching something to this, then I will wait. I should use the same color here. I'm going to attach something here, parent 1, and our idea still works, right? We just go up till we can't go up anymore, and we're pretty much done, right? That checks the thing, and to add an edge, we can just add an edge. By the way, maybe you guys are thinking, oh, why can't I add an edge like this? Won't that break the thing? The thing you need to realize is you could also have added an edge like this. That won't change anything. And we always choose what's better. Isn't this just DFS? I never understood how DSU is O of inverse Ackermann of n. Will you explain that? I'm just going to say it. I'm not going to explain it. I'm going to explain the small to large version. And I'm going to explain this as well. I will not explain why it is specifically the inverse Ackermann, because I can't explain it because I don't know myself. I know that it's gonna be like, I know it's gonna be very fast, and I can explain that really well, but I can't exactly explain the exact function because I don't know that. Okay, but anyway, small to large is another great example. Both of these are good examples actually. Now I'm going to get to that, don't worry. So isn't this just DFS? It's not exactly DFS because we are not doing a DFS from one node and checking if we reach the other one. We're doing a kind of DFS from both of the nodes going as up as we can, and then checking if we have reached the same node. This is actually how we check. This is like how we check if they're the same thing. Because if no, not exactly 2 pointers. This is not exactly 2 pointers. This is just you're just going up. Does this make sense? How do we go up from two sides? You just go up from one side first, and then you go up from the other side, like in like two separate phases, basically. Now, I'm actually gonna code a solution to this. Actually, no, wait. Let's not code this just yet. I want to. One more thing I want you guys to realize is that we're always going to have trees, right? And on every single operation, what we do is we connect two trees, right? We're going to be connecting another tree with another tree. Now, it's our choice if we want to connect it like this or if we want to connect it like this, right? Now, the question is, what are we going to choose to do? What about directed edges? So, oh, directed edges as in this same question, but with directed edges. It's a lot harder than just the SU. And it is also out of scope. In this question, we assume undirected edges, but I'm drawing the edges as directed because I'm just making it so we always get a tree. Okay. So now I'm going to first present the result, or not present the result. I'm going to first ask you guys a question. Suppose I have two trees. I'm going to just get two trees. That we get. So my question is, wait, I haven't even drawn the edges yet. I need to draw the edges. See, this is not a good setup for the question because it doesn't follow me when I go off the screen. Wait, have I gone off the screen? I don't think I've gone off the screen. Wait, guys, can you see what I have drawn? The tree thing. The two trees thing. Yeah, you have, right? Okay, cool. So, basically, I'm asking, am I going to draw an edge like this? Or am I going to draw an edge like this? That's my question. Okay, so how connect small to large? There's no difference from the small to the large. Okay, so I'm going to go with there's no difference because I don't know the difference. I mean, it's both, they'll both give the right answer, right? Why is one different from the other? I mean, I don't see it yet, to be honest. Why are we discriminating based on size? I mean, that's pretty rude. I mean, okay, so I see some reasons. Advik's reason is here. Contest space shows TLE for some reason. I mean, that is a result. It's not a reason, but I guess it's a pretty good motive to connect small to large, maybe. But again, it doesn't really make a difference. Adding something smaller to something larger takes less time. I mean, how does it take less time? I'm just doing parent of v is equal to u, right? This is one line I'm doing. So suppose this is node u, and suppose this is node v. So if I am adding the blue edge, then I'm doing parent of v is equal to u. And if I'm adding the red edge, then let me just get the red color out. I am doing parent of u is equal to v. I mean, both of them are O of 1, in my opinion. We just ball and set parent of u is equal to v and parent of v is equal to u. So that would be absolutely catastrophic. Please don't do that, because then once any single, like every single time you get into u and v, you're just not going to be able to escape, and you're just going to have like an infinite kind of thing. That is probably not what you want. Unfortunately, we have to choose, which is pretty sad. But okay, let's see what some people are saying. If there's O of 1, it should make no difference. When you check connectivity, it is faster. So I'm going to claim that adding the blue edge is better. And I mean, I said I'm going to claim that adding the blue edge over here. Oh, let me get the right color. I'm going to claim that adding the blue edge is better. By the way, what are we discriminating based on? We're discriminating based on size right now, right? And nothing else. We're just adding based on size, right? So we connect the smaller one to the larger one is what I'm saying. So we can actually, I'm not going to tell you why this works yet. I'm actually just going to code this problem up, and we're going to see what happens when I code it up. Okay. So I hope everyone, oh wait, I just realized I'm not presenting, but I don't want to present because that would mean that I lose all of this work. I really, how do I save this? If I press uh save pages template, I can't do that. See, I would have hoped it saves itself, but it didn't save itself last time. So I just I just hope that I wouldn't have to draw all of this again. Okay. You know what? Let's take another leap of faith, and let's just hope it saves itself. Okay. I am going to move on to implementing this. I am not going to. I have never actually justified the small to large thing. I mean, I don't even care about that right now. I'm just going to code what I said before, okay? Everyone can see the question. We have undirected graph. So what is the first number? We have n, right? So int n. Now we have t is equal to 1, t is equal to 0. So this data structure is called a UFDS or a DSU. So I'm going to create a class called a DSU. Okay. I have to maintain a vector. I should just include vector of the parent values, the size of the number of things we have. So this is the number of nodes we have. We have a constructor which sets n, and now we're going to just set the parent of everything to itself to begin with. The reason I'm doing this is because that way we can like detect when we reach the top of the tree. This is like really nothing. I could have chosen anything. I'm just doing this because I define the parent of the root to be itself. Now we are going to have a function we call root, okay? So root means, if I could show you the diagram I drew, that would be great, but I had to close the whiteboard for some reason. I don't know why. But, oh, you have no idea what's going on? Okay, oh my god. You know what, let's not do it with classes then. Let's do it another way. Let's make an array called parent, okay? Do you know what a lambda function is? I am just going to use it over here, because that will mean that I don't need to pass in the thing to. Okay, wait, I actually can't use it because I think it will confuse so many people. So I will make it over here instead. Okay. So like I said, we set every single parent of I initially to I. Right now, I hope now people are understanding, right? I don't want you to not understand just because I'm using advanced C++. Bro, it's a matter of time. That's the only thing. I hope people are understanding now. Are people understanding now, or is the answer still no? Okay, you are understanding now. That's great. Understand? I think I understand. So the reason I'm saying parent of I to I, you will see why I'm doing that when I code the next function. The next function is the root. Okay. So the root in that tree which I drew a tree where I was going like 1 is connected to 2 is connected to 3, and also 5 is connected to 4 is connected to also 3. Right? I think I can make this a bit better if I. So it's like both of these are going into 3. Okay. So in this case the root of the tree would be 3. Like, do you get what I'm saying? So this function over here is going to find the root. So how I said you need to just go up a lot and you need to check if the thing we go up to ultimately is equal or not. That's what I'm doing over here. So now why I did parent of I is equal to I is because now if we are at the root, notice that its parent is going to be equal to itself. It's a very easy way to check if we are already at the root. That means we don't need to go further, right? Otherwise, we need to set u to parent of u, and we need to return the root of that. It's a recursive function. That means from 1, I will go up to 2. And then I will say whatever I get to 2, that's the answer to me. You get what I'm saying? The nodes are from 0 to n minus 1. Oh wait, are they from 0 to n minus 1? Oh my god, they are. That's actually my mistake. I thought they were from 1 to n. So we don't need n plus 1 here. Thanks for pointing that out. You actually, yeah, this is 0 to n. Okay. So does everyone understand what this function is doing? I'm not saying why, like, understand why we need it. Do you understand what it's doing? What it's doing in brief. So, imagine we had a tree like this. You're understanding what this like tree means, right? This diagram. So if I say root of 1, I want it to return 3. If I say root of 2, I want it to return 3. If I say root of 4, I want it to return 3. I just wanted to return like the uppermost node you get by continuously going to the parent. So that's basically what I'm doing here, right? No, I think actually if I implement it without recursion, that would be like a bit easier for people to understand. I can also say while u is not equal to parent of u, u is equal to parent of u, and return u. I can do this as well. It's the same thing. Maybe you can understand this better. So while it's not equal to itself, while the parent is not equal to itself, like the parent will be equal to itself, but there's nothing above it, right? Uh, while that's not the case, I go up, and then finally when I know how I've reached the root, so then I just return it. Right? Does this make sense? So and the parent, because only the root is its own parent. Yeah, exactly. Yeah. Recursion is easier to understand. That's actually a bit surprising. I would have found. How is the root its own parent? There's nothing fundamental about it. I just defined it so the root is its own parent. There is like there's really no reason for it. It's just that I like implementing it like this. That's the only reason. Yeah. But again, I would suggest that you define the root to be its own parent because it's a very nice way to implement it. Okay. So did you guys understand what this function is doing? Again, same question. Not necessarily why we need it, but what it is doing. Yeah. We have a bunch of yeses. Okay, that's great. Now, how do we check if two things are in the same component? Like I said, we have to go up. We have to go up the tree. I need to find if they end up to the same root, right? So now that's actually why we need it. If root is the same, then they are connected. That's exactly the point. So, were there any doubts about this? Any doubts about, oh, why is this always going to work? Or like, you know, or are you guys actually, are you guys convinced that yes, this is gonna work, you know? The reason it's going to work is because it's a tree, by the way. That's the reason. I feel like sometimes it won't work. Okay, that's exactly the right question to ask, because that's what actually checks. So I'm happy that so many people are convinced. I'm also happy that someone is not convinced, because that gives me the opportunity to, you know. So the reason it will work is because it's a tree. Think about it. Imagine a sense, like imagine a bunch of disconnected trees. I'm saying that if basically we are now checking if two things are in the same tree, right? So if two things are in the same tree, then they are always going to have the same exact root. The two random leaves have the same root if they are in the same tree. Yes, yes, always. And if they are not in the same tree, then they will have different roots. They have to have different roots. That's the reason it works. It's not like anything random. And it's also not super intuitive, I feel, if you haven't seen like a tree before. Yeah, a tree has exactly, in this case, it's like we're directing the edges up, so our tree has exactly one root. The connecting part is going to be difficult. Okay, so let's actually code the easy part then. Bool is connected int u int v. If root u is equal to root v, return true. Otherwise, we return false. Right? Very easy. Very, very easy. Very easy. Now, how do we connect two trees? Again, I wish I could pull up that diagram, but I really hope you guys have it in your mind, the one with the red edge and the blue edge, right? I really hope you guys have that in your mind. I'm gonna call that function merge. Alright, you can call it connect, you can call it anything. All I'm going to do is I'm going to set u to the root and v to the root. The reason I'm doing this, by the way, is because connecting a leaf and connecting a root are like the same thing. And I want to connect the roots just to maintain the fact that they remain trees. Okay. Now if they're already in the same component, then we can just return early, because that means they're already connected, right? We don't need to connect them again, right? Otherwise, we're going to set the parent of v to u. But we could have also set parent of u as v. It doesn't make a difference. I'm just going to set the parent of one of the roots to the other root, exactly as that diagram I drew before. Very easy, right? I zoned out, give me a second. Okay, I will show you the code again. I will explain it again as well, actually. I'm saying that I can always connect two things by connecting the roots in the tree they are in, because it's like my choice however I connect them, right? So I'm just choosing to connect like this. And actually the reason I'm doing it like this is because I want to maintain that they continue remaining trees. Then I'm saying that if u is v, then they're in the same component, like we already saw over here. That's why we just return. And otherwise I'm setting the parent of v to u. So if I have like u here and v here, I'm setting the parent of v to u. Back to the old question, this seems pretty simple. How is the red blue thing making a difference? I mean, I don't know how it's making a difference just yet. For now, we're just going to try to get a working solution to this using this convoluted concept. Let's see. So we have n and q. So for each and every query, we have a type. If the type is 1, it's 1 and 2, right? Yeah. No, it's 0 and 1. Type is 0, else. Okay. So if it's type 0, we need to add an edge. So that's like saying merge, right? Otherwise, it's if u and v are connected, print 1, otherwise print 0. So that is connected. Right? I think this should work. Let's actually test it out before I affirm that it works. So it's giving the right answer, right? So let's go ahead and submit this. I mean, let's just go ahead and submit this and see what happens. Mm, okay, so we're getting AC. Getting AC. So far we have. Okay. So we got AC on a lot of them. We got a TLE on one of them. Hmm. Hmm. And the other one is taking so long to judge that it's not even. I can't even see the verdict. It's like probably a TLE, but basically the consensus is that we got a TLE. Okay, so that's pretty annoying. I don't know what I exactly did wrong, right? TLE, 5 characters added in AC. So that's pretty sad, right? It's a pretty unfortunate that we got a TLE on this. Now I'm gonna show you guys one way that I think this will fix it. Uh, so basically this is just saying half of the time we merge you with V, otherwise we merge V with you. As we said, it doesn't make a difference. But hey, since we're getting a TLE, maybe we can add random stuff and see if this works. Let me see. Let me see if this works. I don't know, man. Even I'm just trying stuff out. So let's see. Hmm. Okay, we have ACs. Some ACs. ACs. Hmm. Okay, we still get a TLE. That's pretty unfortunate. That's pretty unfortunate, right? So we have tried so much stuff, and this thing is just TLEing. What can we do? Now we go back to the idea. Actually, even I expected that to pass, not gonna lie. That should have ideally passed. Wait, is it the fact that I don't have fast IO? Maybe that is the case. This should have passed. Maybe it's the fast IO. Let's actually try that. Yeah, you know what? Let's give that another shot because I feel like maybe this should work as well. But maybe not. We'll have to see. Hmm. Okay, AC so far. AC so far. Hmm. Hmm. There was already AC in these. This is the real test. Okay, it does still TLE. That is actually pretty unfortunate because I feel like this actually ideally should AC. But okay, that's okay. We tried a lot of things and it didn't AC. That's okay. Now we're going to try saying what Advik was. We're going to try doing what Advik was saying before. Maybe my luck is bad. I don't know. I actually feel like the randomization should work. So I don't know, man. I don't think I've done any of it before. But okay, but like being for real, Treeps use almost the same trick, the randomization trick, and it does. Oh wait, no, I know what's different with Treeps. I know what's different with Treeps. I know how to make this work, but I'm not gonna go into that because I'm not going to go into that because let's just do what Advik suggested instead. Uh, which was I think a lot of people also talked about it. You guys are saying something like small to large, right? So what we are going to do is we're going to make another array called size. We're going to do size.resize n, and size of I is equal to 1. Initially each thing has only one node, right? So size of I is like it's the size of the component. Oh, I can't call this size because st. No, I can call this size. Why is it? What's going wrong? Oh, I need to call it something like SZ because I'm using STD. Okay, cool. So okay, now I think this should work, and I think my VS Code is just out of date. Let's just check by compiling. Yeah, okay. So now I'm saying let's do exactly what you guys were suggesting. Some of you were suggesting. So when we set parent of V to U, then the size of U increases by how many ever nodes we added, which is the subtree of V, right? So we're going to do size of U plus equals size of V. And now what we are going to do is over here, we are going to, oh, it's not called size, it's called SZ, my bad. What we are going to do is we are merging V into U, right? We are merging the subtree of V into the subtree of U. So we're going to say if the size of V is greater than the size of U, then we swap U and V. If the size of V is greater than the size of U, then we don't want that. We want to merge small to large. So now after doing this, we make sure that V is the smaller one. And we're merging it into U. Okay? This is like very random. I mean, the only reason I am adding it is because so many people in chat over here suggested it. That's literally the only reason I am adding it. I think the random. No, by the way, Advik, I know why the randomization didn't work. But it's because you need to assign a priority to each node, instead of what do you say? Like, and you need to use that same priority to compare. You can't just randomly do it. It will be adversarial in the case of like lines where you specifically choose merges. That's the thing. No, that's also not fine. Okay, anyway, so like I said, I only added this because so many people over here told me to. And wait, I didn't make a mistake here, right? If size of V is greater than size of U, now size of V is less than size of U. And so we set the parent of V to be equal to U. Yeah. So now let's just try submitting this. Let's try submitting this. Let's see what happens. Okay, we're waiting. We're waiting. Okay, finally started judging. Okay, so far at ACs, it's ACing. Oh my god, that AC in 31 milliseconds. What the hell? What? Okay, that seems very weird. What the hell? I mean, we just did a super random thing, bro. I'm not acting, bro. I don't know why that AC is. I mean, I literally just added something super random which shouldn't even matter, and for some reason it went from 5,000 milliseconds to 30 milliseconds. That's pretty insane if you ask me. I mean, even I didn't expect 31 milliseconds. I actually expected something like 400 or something. So I am a bit genuinely optimized. Genuinely surprised that was so fast. So that's pretty crazy, man. I mean, honestly, I don't even know how to explain this. I mean, I don't even know what's going on. Hmm. Okay, let's try to think about what's going on now that maybe I've convinced you that maybe it's not the same thing. Like some people are pointing out, we initially thought it was the same thing, but I mean, the results show that maybe it isn't the same thing. Maybe this line is really doing something useful because if it wasn't, then we wouldn't get such a fast AC, right? So yeah, why now the next question is why is this happening? So to explain that, I'm going to go back to the whiteboard. Uh, and hopefully my whiteboard is saved, and it seems like it isn't saved, which is just really unfortunate. I went to my whiteboards and there's no data. I went to recent, there's no data. Okay, whatever. I'm just going to open another brand new whiteboard. That's fine. Yeah, GG indeed. So, but that's fine. I will turn off this. I will turn off this. And there you go. Yeah. He was just too scared of the technique, bro. You know. Okay. Anyway. Uh. Now my argument is that somehow maybe this is like really good. I want you to think about this. What is the total sum of size of u for u 0 less than or equal to u less than n? What is the total sum of this size? If we exclude the and u is a root, Anyone here can answer? Okay. My question was, what is the total sum of the sizes of 0 less than or equal to u less than n and u is a root of the size of u, as we defined it in our thing? Yeah, it is n because there are n nodes in total, and each node is going to be part of at least something, right? So it's always going to be n. Right? So our total sum is equal to n. Now we have another question. It is n because this is just a fancy way of saying the sum of all of the root subtree sizes. And if we look at all of the roots, that's all of the nodes, right? Initially we have these disconnected nodes. Then if I connect this, then the size of this is 2. The size of this we don't care about because it's not a root. The size of this is 1. The size of this is 1. If I connect this, then we don't care about this size. The size of this is 3. You get the point, right? Now I'm going to ask another question. By the way, how do you type on this? I think okay, instead of that, I will send this code here. Actually, I don't know how I want to do this. I don't know the best way I can do this to make you guys understand. Okay, you know what? I will ask another question. I will ask, let's say you have a node u and you make it equal to 2u, or let's say you have a number x and you make it equal to 2x, and you make it equal to 4x, and then you make it equal to 8x, then you make it equal to 16x. You get the point, right? My question is, how many times can this happen if the maximum value of x is n? Yeah, the answer is that it can happen log n times. This can at max happen log n times, right? You got AC using randomization. What did you change, by the way? Like, what was the difference? Did you just use the priorities thing, or? Like, so yeah, priorities thing. Yeah, makes sense. That's the same. That's the same trick we use for treeps actually. So that makes perfect sense. Okay, cool. Uh, anyways, so like I said, this can happen max log n times, right? Now I want you guys to look at this code over here. This is actually very interesting. Specifically, I want you guys to look at what happens. Now I want to define a new term. Let's call it size only. And I'm saying the size of any node in general is the size of the root, basically. So the size of a node is the number of things in its thing. So basically, if using that definition, if I draw a tree like this, if I just draw a node over here, oh, oops, I accidentally went to something else. Yeah, then the size of this is 3, this is 3, this is 3, this is 3, and this is 1. So do you get what I'm saying? Do you get the new definition of size? Now my question is, when I merge a node with something else, do you see how we always guarantee that size of u is less than size of v? Oh wait, my bad. Not this. We guarantee that size of v is less than size of. No wait, do we guarantee this? Yeah, sorry. We don't guarantee this. We guarantee the other way. It's just a technicality because I wrote it as the different swap. But we basically always guarantee that size of v is less than size of u, right? Because if it's not, we swap it. Right? Yes. So do you see how after that what happens to the size of every single node in V? After that, every single node in V gets a new size, right? After that, every single node in V gets a size equal to size of V plus size of U, original size of U. Like whatever this was before. Right? That becomes the new size of every single node in V. But now do we see how size of U is actually greater than size of V? So this is actually greater than, so this is actually greater than size of V plus size of V. Do we see how that's true? Roughly how much longer is the lecture since I have to finish a project? I think it will actually extend to around like 10 o'clock. But I'm going to have a break after I finish explaining this, like a 10-minute break, because it's going to get pretty heavy otherwise. Anyway, so size of V plus size of U is greater than size of V plus size of V, right? So do we see how size of V goes from being size of V to being size of 2V on every single merge? Or sorry, 2 times size of V on every single merge. So now I'm saying that every single time I move a subtree into another subtree, I'm only ever doing it. And sorry, whenever I do that, I double the size of it. By the way, you may ask, oh, we are not changing the size of U, doesn't that break things? It doesn't, because I'm talking about the total number of times you move an element. That's why it doesn't break it. And we're only moving the things in V to be under U, right? So it's kind of like we have U already over here. And we have like V over here. We have like U over here. And we have V over here. And we're adding it like this. So basically, every single node, whenever it is moved, I'm saying moved because that's very important. Whenever it is moved, its size doubles. Do we guys see that? Do we see why that's happening and how that's happening? And do you remember how we concluded that this doubling process can only happen log n times? So this is actually why the total amortized time complexity of merging across all operations is actually equal to q into log base 2 of n. So in fact, this is actually another application of amortized analysis, which is why I again thought very relevant example to include here. Oh yeah, definitely going to include that as well. That's actually a pretty funny, very funny technique. But I hope you guys understand this. I mean, before we thought that the reason is so mystical, right? I mean, it changed from 5000 to 31 milliseconds, which was just insane. But now hopefully we understand. Maybe we don't find it intuitive, but hopefully we understand why this is happening. We can justify it after the fact. I hope this part is clear, because it is actually a bit confusing. So if it is not clear, please let me know. Can I summarize it again? Okay, let's see. So basically, what is my thing? I have a thing over here. I have a tree whose root, actually let me draw a better line. I have a tree whose root is u, okay? And every single node over here has the size of u, right? Every single node has the same size. I'm talking about the size of the component it is connected to, right? So I maybe have something like this. I'm just drawing something random. And now I have another node over here that's v. This is v. And again, it has things connected to it. So basically what I am saying, we asked the question, am I going to draw the edge this, or am I going to draw my edge like this? Which one is better? So I'm saying that if we draw the green edge, then that's like we're thinking about is we're moving these nodes, right? Like we're moving their ownership from being over here to being over here, and therefore we are increasing their size, right? Well, in my head we're picturing that. We're not actually coding this up. This is the part of the proof. We never actually move them ourselves, but this is what we need to imagine to justify why this is very fast. So I'm saying that we are moving all of these nodes ownership from being here to basically being owned by this node, right? And therefore, implicitly, we are increasing the size of every single node. We are implicitly increasing the size of every single node, the size of v plus size of u, right? And size of u is always bigger than size of v, so we essentially at least always double the size, right? So let's just say we increase it to 2 times size of v. Now realize that we actually can only do this logarithmic many times. That means that the number of times we do this rerouting operation is going to be log of n. And that's why the height of the tree is also going to be log of n. Do you see why that has to suggest that the height of the tree has to be log of n? Because the height only ever increases when I do this, right? That's the only time my height increases. Now I'll increase the height by 1. If I reroute it again like this to some other node, now the height is like 1 green edge and 1 blue edge. So now the height is 2. And suppose we only ever do this log n times, now the height is also going to be log of n, right? That is exactly why this is very fast. And this trick is called small to large merging. So this is actually a very confusing concept. So I hope some people actually understood this. That would be very great if you guys did understand. If not, I'm going to give you guys a break soon for like 10 minutes, after which we're going to continue with 2 pointers. Before the break, I'm going to show you guys something pretty interesting. So just going to remove this. I'm going to remove this. I'm going to remove this. I am going to remove this. I'm going to remove this. And I'm going to go back to the recursive implementation. So if u is equal to parent of u, return u, return root of parent of u, right? Now over here, what I'm going to do is I'm going to add 2 characters here. Oh sorry, not 2 characters, 5 characters specifically. Is it 5 characters? It's 1, 2, 3, 4, 5, 6, 7. Oh, it's technically 7 characters, I guess. Yeah, we're gonna add 7 characters here. It's obviously still gonna give the right answer because this won't change anything structurally. It won't change anything like this. We're gonna go here and we are going to submit.
Yo, we cannot see your screen.
Oh my god, that's very bad. I thought I was sharing my screen. Okay, hold on. The whiteboard is unfortunately going to end again. Yeah, wait. I need to close this and open. What is the link? Yosupo Union Fine. There it is. You can see my screen, right? So all I said is that we have this implementation. We add these lines to it. Parent of u is equal to this. That's pretty much it. Okay, it's 7 characters because 1, 2, 3, 4, 5, 6, 7. We add 7 characters. And we actually remove the whole size thing. So let's actually see if we can submit this and what exactly happens when I submit it. Hmm. Hmm. Okay. Okay. Oh. Oh, say that also gets AC in 31 milliseconds for some reason. Okay, that's cool. So you can also do this basically. That's the point. For some reason this works really fast as well. Just adding these 7 characters in our previous implementation, where I didn't do any of this size reasoning, basically absolutely annihilates this problem, and now it's also 31 milliseconds, but the core is just so much shorter. Why does this happen? I don't know. I don't know why this happens, but for some reason it happens. Anyway, with that being said, I'm now going to give you guys a 10-minute break. I am going to start again at 9:05. If you want, you guys can think about this during the break. Yes, we are done with UFDS. Guys, if you want, you guys can think about this during the break or maybe for homework. Why this works, you know. Submit with rank. What do you mean by with rank? Wasn't the previous thing I did with rank? Bro, that's so unnecessary, bro. Anyway, by the way, this technique is called path compression. So anyway, I'm going to start the break now. Please take like these 10 minutes to eat something, drink water, and stay refreshed. The next part is going to be the easiest, by the way. So UFDS and amortized was the hardest part, and now 2 pointers is going to be relatively easy compared to this. So yeah. Okay. Hello everyone. uh just check that the recording and everything is still working. Yeah, it's all working. Cool, great. Okay, yeah, so hello everyone. I hope everyone's back and done with the break. Uh okay, cool. Great, great, great. Okay, so the next thing we are covering is 2 pointers, and fortunately, like I said, this is going to be a lot easier than UFDS. So of course we love easy at the end because we just thought a lot, you know, and it's probably nice to have something that's a bit more relaxing. So we're going to look at some pretty easy 2 pointers problem. They are in the Code Forces Edu section. The entire course is pretty nice if you guys want to do that as well. I'm going to be covering all 3 problems from here in step 1 and 1 problem from step 2. So we're just gonna jump right into it. So here is the first problem we'll be doing. Again, like always, I believe in teaching by example rather than saying a lot of theory at first. So and this is 2 pointers, so we're just gonna be jumping right into it. So everyone please go ahead and read this problem. Yeah, this is another amortization, yes. What is the level till which we have to learn DSC for ZCO/INOI? Oh, everything I said this time. So do you remember that at the end I gave you that one code? It says no such course. That's weird. Okay, hold on. Anyway, I'll just answer this question first. Whatever I taught in the lecture, even if you don't do the small to large thing and you do the, if you do the 7-line addition thing I told at the end, even that is fine. Even whatever I told you right now is fine. That's basically the level. You don't need to learn much more than this. I think yes, you do need to join what Alvik said to be able to access these problems. I think this is just a edu section page. So if you just join that, you'll be able to read it. If not, I am anyway going to start sharing my screen so you can read it from there as well. So can everyone see my screen? Yeah, people can see my screen. Okay, so this is the problem. Wait just a second, I hope. Yeah, yeah, cool. So I don't know how many people saw the discussion we had on. I don't know. I think someone asked me about like what the optimal strategy uh for doing graphs in DP was, and I think someone said that they're going to finish the entirety of graphs before moving on to DP or something like that, and I said that this is a bad strategy. So this is kind of the same question. I mean, it's not the same thing because over there we assumed something else, and even if you weren't there in that discussion, that's fine. But basically, it's asking the same question in spirit. We are given two sorted lists, and we just need to print the culminated sorted list. And they have said in the question that you can do it in n log n time, but you should try doing it in O of n time. So print sorted a plus b is obviously correct because that's what the question basically asks, right? So we are going to we're just gonna like not sort, and we're gonna do it using 2 pointers. Yeah, exactly. So how do we do this using 2 pointers? Basically what we are going to do is, well, we know that the smallest element of the array has to be between 1 and 2, right? So it's definitely either this or this, so that's what we're going to fill in for the first element. Then for the second element, now we already used this element up, so now we are looking at these two considerations for the smallest element. A quick question, why do we only need to consider these two? Yeah, why do we only need to consider these two? Yeah, the smallest is always going to be one of them, because everything else, everything over here, over here, over here, like 9, 13, 18, 18, they're always going to be bigger than 6. So we only need to consider the smallest of the elements at the front of the array, basically. Does everyone get that? Two pointers, one at A, one at B, and we put BJ and increment J. Yeah, that's basically what you do. So now I will show you how to code this. I mean, hopefully everyone can code it already, but I guess I'll show you how I code it. So let's just remove this code. We can remove this. We can remove this. So I'm going to explain what I'm doing from now. This I didn't explain anything because it's just taking in the input, right? What I'm going to say now is if our pointers are at such a position, if our pointers are at such a position such that both of them are in bounds, so this will happen. Like, let's say we have a case where we entirely traverse this array and now we are just on this array, then we just have to add everything over here, right? So my case is saying that right now both of the elements have a valid candidate element remaining. While that is the case, what I'm going to do is I'm going to choose the element. How do I like how do I show this? I am going to choose the element. So if a of I is less than b of j, then I'm going to do I plus plus and c dot push back a of I, right? I need to do this first, and otherwise I'm going to add BFI and, oh sorry, not BFI, BFJ, and we're going to increment J, right? Now, while I itself is less than n, we just need to push back AFI and increment I. Now this is assuming that J is now completely over. So we just have to add the remaining elements in I. Similarly, we'll do the same thing for J. And now we can just print the answer at the end. And I think this should work. Let me just test it out. Yeah, that seems to be working, right? Don't realize how good I feel. That's so true. Okay, let's see. Using set to sort and sorting it normally takes the exact same time complexity. Yeah, time complexity is the same, but the constant factor is higher when you sort. Lecture should be put on YouTube like pretty much instantly after I finish lecturing, cause, or maybe it will take like 3 or 4 hours because processing and exporting and stuff. But yeah, and I'll have to edit some parts out. But yeah. Okay, so anyway, yeah, I hope that doesn't happen this time. I mean, I think I figured out what went wrong, and so it shouldn't happen. But okay, cool. That's fine. You can watch the recording then. That's cool. Yeah. Anyways, so like I said, this code works. Does everyone understand why I am doing like these kind of for loops like this? Yes. Okay. So this is our solution. It will work. I'm not gonna submit it because I mean, there's no real point. Or you know what? Fine. I will submit it. Let us submit this. Okay. So I can't submit it because Codeforces isn't working. Or is it working? Let me just try once more. Okay, it is working. Cool. I will just submit this time. And I don't know, there may be a queue because I think there's a contest going on right now. Yeah, that's probably why there's a queue. But well, I am just telling you guys this will work. Now, just in case you actually need to solve a problem like this in the in like contest, there's actually a very nice trick to this, which I will show you right now. No, not -1. It's just this. The trick is that there's this function called merge, which I mean kind of does what you'd expect. And if we compile this, oh, what to include the header file algorithm, then you can see it has the exact same output. So those are two ways to solve the question. So our opinion on define endline, you can do that. That's fine. I personally don't define a bunch of things, but because I don't really like them. But yeah, it's fine. But I don't really personally do it. Submit without running. No, I did run it, right? I guess I did run it. Yeah. Yeah, and interactive as well. So I mean, I don't know. I just personally don't do it. Okay. But everyone got this, right? This is very easy, very nice, very confidence boosting as well. And also hopefully you learned that this function called merge exists. We actually go here, you'll see there's some crazy stuff going on. Okay. You'll see it actually, if we ignore the crazy stuff, it actually does the kind of the same thing. while first one not equal last one and first two not equal last two, if compare, then we set the value and we increment the pointer. If else we do this, and so it's actually the exact same code we had. It's just that it's in the standard library. Okay, that's the first question. The C++ standard library authors wrote that. Now let's do the next question. Can you guys access the question? I'm just gonna put it in screen again. Yeah, these are all 2-pointer questions. Yes. We're gonna start off easy. And we're gonna end easy as well, actually, because there's actually nothing really hard in this. There's just one question which I feel is somewhat interesting, which I am going to cover. Otherwise, everything is like pretty easy. So the question is, you're given two arrays sorted in non-decreasing order. For each element of the second array, find the number of elements in the first array that are strictly less than it. So we have like 2 here. So the answer is 1. We have 3. The answer is 6, 9. No, sorry. For 3, the answer is also 1. For 8, the answer is 6. And so on. So what are the ideas people have for this question? Print I before increasing j. I mean pretty much, yeah. But like that's very ambiguous, you know. But my real question is, does anyone over here think that we would use binary search to solve this? No people thinking binary search, right? Binary search is possible, yeah. Not like it's wrong, but 2 pointers is going to be faster, more intuitive. I don't know about that, but like sure, yeah. So anyway, the binary search method to solve this is just to print like upper bound, because upper bound will give you the index of the next greater one, which will correspond to the count of the things less than it. I don't know, if you want I can show you that, but actually I won't, because this is about 2 pointers, so we're just gonna cover the 2-pointer way. So the way we do this now is we are going to keep a pointer to the first element, to the first array, which will basically store the index of the thing that is like the index of the thing that is currently less than us. What we need to notice is that as we traverse this from left to right, as we traverse this array from left to right, the pointer of the element will only ever increase. So it will go from here to here to here. It will never like actually decrease. Right? So what we are going to do is we realize we just set a pointer over here, and if the pointer is over here for like let's say 8, then that means our answer is that pointer plus 1, because that will, we are just converting index to count. Did everyone like understand the solution? Yep, exactly. Okay, cool. So I'm just going to code this real quick. Maybe I'll call this j because it's the second array. We're going to say while I is less than n and a of I is less than b of j, then we're going to do I plus plus, right? Actually, there's an edge case I just thought of, where we can have a case number of elements in the first array strictly less than yeah, so we actually have to print min of I plus 1 and n. I think this should work though. So wait, but I less than n already ensures. Oh yeah, okay. So we need to print min of I plus 1 comma n, because if I is equal to n, then we can't have n plus 1 elements. But that's just a small edge case. And I think this should hopefully work. The same array only. Okay, that's not a good thing. Why is it not working? Oh, wait. This is now, while AFI less than BFJ, we're gonna get the next element, so we actually just need to print I. Okay. We don't need to print that, we just need to print I. And now this should work. Okay, cool. Yeah, so okay, now that you're saying submit, I feel like I feel like you think that this is a wrong answer. So I'm going to check it carefully before submitting. Hmm. Hmm. You know what? This seems fine. This seems fine. Let's just submit. If it's not fine, we will maybe find out after the div 3 or something. But anyway, I think you guys either way get the idea. So, and I feel like this is correct. Uh, so let's just submit this. Okay, by the way, the first thing was actually correct, which is nice, I guess. Okay, cool. Now let's move on to the next problem. Problem 3. Okay, so has everyone read the problem? Yeah, frequency table is probably, yeah, UFDS and DSU are the same thing, by the way, just different words for the same thing. Yeah, frequency table is something that I would also do. But since it's 2 pointers, they want us to do O of n, so I guess we should do O of n. I haven't coded this yet. I haven't coded any of these questions yet. You could see I had no submissions, right? Uh, okay, but that's fine because, oh, is frequency table not allowed? I mean, you can just do coordinate compression, right? Beforehand, but then you'll get the log again. Or you could use unordered map, which I am not sure if it will pass or not, but maybe it will. So again, sets introduces log, so that's the issue. Okay, so because of this, I am not going to code the unordered map solution. I'm going to code it with 2 pointers. So the key thing to realize is that, well, there are multiple ways we can do this actually. I'm just trying to think of which is the best one to do. Okay, so there's actually a very nice way to do this, and that is we're gonna have one pointer where a of I is less than or equal to b of j. So that means that when we reach a 3, this pointer is going to like quote unquote converge to this value. Or no, wait, is it going to converge to that value? No, that pointer is going to converge to this value, right? And we're going to have another pointer where we have a of I less than b of j, which is going to converge to this value. So now our pointers basically span this range, right? And now the answer is just j minus I. Or the answer is the difference between the 2 pointers. Of course, we will also have to check whether the element is actually equal to our element. That will be based on like pointer 1. Did everyone understand what I'm saying? How do I get rid of my skill issue of 2 pointers? I can get the algo down, but implementation I mess up. Yeah, so implementation is always the hardest part in like 2 pointers. So let me see if I can implement this nicely actually. So we are going to have in pointer 1 and pointer 2. So you know what, I'll again call this j just because it's referring to the second array, and maybe that's more intuitive. So now like I said, the first pointer is going to be and this should be m, not n. Or the first pointer is going to be a of, also it's not I, it's pointer 1. A of pointer 1 less than b of j. This is the first pointer. The second pointer is the exact same thing, except we have less than or equal to over here. Now, if if b of j is equal to a of pointer 1, and pointer 1 is not equal to n, then we can add to our answer pointer 2 minus pointer 1. Actually, this doesn't have to be n64t. And I don't even need a total. Wait, do we want a total answer? We do want a total answer. Okay, so then this is what we need to do. I think this should work. Let's see. Okay, so this seems to be working. I guess we're gonna find out if it's correct. It should be correct though. Hmm. Both of these are still in queue, but that's okay. Now let's move on to step 2, which I'm only going to do the first problem of. Where is it? Yeah, it's here. And after that, I'm gonna cover the interesting technique I was alluding towards. We're setting pointer 1 to the first occurrence and pointer 2 to the last occurrence. So we're not setting pointer 2 to the last occurrence, we're setting pointer 2 to the element right after the last occurrence. Yeah. That's the most natural way to code it. It's like what results in the shortest implementation, basically. Yeah, this is correct, by the way. This is the reason. Uh, is this sliding window? Let me see. I think it is, yeah. Well, no, this is not sliding window. I mean, okay, yeah, technically I guess it is, but it's still 2 pointers. They're both the same thing, really, in my opinion. Okay, so has everyone understood, read the question? Probably is interesting. Okay, I'll just give more time then. I'll just give you guys like some more time to read the question. Okay, cool. So basically this is the exact same thing as the previous question, but now we just need to move our right pointer ahead. So I'll call my right pointer j in this case, and I'll call my left pointer I. So I need to move j ahead only if we are like currently still in bounds. So then after that, at the end, my j will point to the element that just breaks the bounds, right? So in that case, my answer will be j minus I, not j minus I plus 1. So it's like almost the same idea as this question. So over here, I don't actually, oops, the elements are themselves between 10 to the 9. Yeah, I don't have this. I'll just erase this code. Longest good segment. Uh, so we're gonna say while j less than n, and we'll have to store the current sum as well, actually. and sum plus a of j is less than the total sum. Then we do j plus plus. Do we understand how this is working? And then we just do this to to our answer. Yeah. Do we understand how this is working? Actually, before I say that, I should probably test that it's correct. How do I compile this? Close all of these and okay, yeah, seems to be working. Yeah. So sum is basically, yeah, sum is like kind of a sliding window of the current sum of the window we are at so far, and we can always extend the window ahead if our current sum is less than s. So if the window included to our sum will be still less than s, then we extend it. So basically this is going to continuously run, and j is going to end up at a state where our sum is actually bad, like we can't extend it more. That's why we do j minus I at the end. It turns out that doing it like this is very nice for implementation. You don't need to prefix, but yeah, you could have prefixed as well. But you don't need to. Uh, if you prefix, then you would have done a of j minus a prefix of j minus prefix of I minus 1 is less than s, which is also fine, I suppose. So did everyone understand this? Wait, I should submit it as well. Hmm. Yeah. Anyway, is this question clear? Did my previous code get AC? That is a good question. Let's find out. Because I may need to fix it. Okay, the third one got AC. The second one is still in queue, which is actually very interesting. I don't know if they're using a regular implementation of a queue, given this abnormal phenomenon. But yeah. Anyway, uh, they should be correct. I mean, I don't see anything wrong with them. But yeah, I mean, it's not even a queue at this point because I submitted something later and it somehow got judged before something had submitted earlier, and it's like in the same contest as well. So I really don't know what exactly was going on there. But I mean, it's fine. Anyway, you guys understood this question, right? Great. Now we're gonna actually go to the nice trick I was talking about. So let me actually open up CSCS. It's not this question. Oh no, it is this question. Okay, cool. So this is the question we're gonna do next. So this is actually very interesting because I claim that you can solve this in linear time, not like n log n or something like that. By the way, I'm giving you guys this question for homework. Uh, this one homework, and so is this one. And so is this one. Oops, I accidentally pressed on something. So is this one. And once I teach you guys how to solve this, even this is actually homework. So yeah, cool. Yeah, anyway, so this question, it's actually pretty interesting, right? I mean, the task is like very easy to understand, but does anyone have any linear time ideas for solving this? Or let's leave linear time. Does anyone have any ideas to solve this? Like, none doesn't have to be linear time. Basic sliding window is O of n log n. Yeah, basic sliding window has a log factor. So there's actually something about OR that's there's something about OR that doesn't let us actually there's something about OR that doesn't actually let us do the regular sliding window pattern. Uh, there's no inverse operation for an OR, right? I mean, once you do OR, you can't really reverse it. Yeah, you can't undo an OR. So if you're moving our window from here to here to here to here, we won't be able to remove the element we just added over here. Now, how do we do it in n log n to begin with? Well, we can actually, yeah, exactly. You can store the count for each bit, and then you can say that the value is if the bit is more than if the value of each bit, like the count of each bit, is more than 0, then the bit is on. Otherwise, it's off. Because if we do it like this, then we actually can undo it. Okay, yeah, I will explain that. And to explain that, I will need a whiteboard. Of course, my previous whiteboard is definitely not there anymore, but I've learned to accept that. Okay. So what I'm saying is, generally speaking, OR cannot be undone, right? But we can kind of work around this and make it so we can undo it. And the way we do that is generally OR is like, suppose I have 1 0 1 1 0, and I OR this. So I OR this with 1 1 0 0 0. I'm going to get an answer such that each bit is 1 if at least one of them is 1, right? So I'm going to get 1 1 1 1 0, right? Yeah, exactly. So our idea basically is that instead of doing this, what I'm going to do is I'm going to remove this OR, and I'm going to replace this with a bitwise sum. So I'm just going to say bitwise. Apologies, guys. I actually do not know where the text tool is, so I kind of have to do this. Okay. I hope you guys can understand that I have written bitwise sum. So basically, this is going to be 2 1 1 1 0. Yeah. So basically, the advantage of this is that now we can look at each one of these bits individually, and we can say that it is a 1 if the thing is greater than 1, and otherwise it's a 0. Oh, sorry, it's a 1 if it's greater than 0, otherwise it's 0. And this will allow us to reconstruct the original number, and now we can remove the last element because now we can just subtract it off. That's the good thing about this method. Yeah, you just subtract it, and each addition is going to be log of n, each subtraction is going to be log of n, its reconstruction is also going to be log of n, where n is actually the number of the size, max size, not the size of the array. But yeah, so this is the n log n way to solve this, and I think actually if you solve this with this way, you'll actually get AC. Because because there's constant factors can be optimized a lot if you, like, for example, use an array instead of a vector over here, which, by the way, now that I mention it, this is like one of the cases where using an array will be faster than a vector, when you definitely, like, it's like a very small size of 30, right? So there's this thing called std array you can use, which again Samik already covered in this lecture. Oh my god, I somehow got the text tool. How did I do that? Oh my god. Wait. Oh my goodness, that's a discovery. Wow. That's very nice. Oh my god, that's amazing. Oh, I don't need to type. I don't need to accidentally left the meeting again, but that's okay because I learned something really great before having left the meeting. So yeah, it was worth it at the end. Wait. Let's just do this. So I can draw and I can add text. Yeah, perfect. So now, like I was saying, std array, you can do something like array in 30 for each and every one of them. And subtraction, you'll just do with a loop of size 30. Addition, you'll do with a loop of size 30. And everything will just work. And I haven't actually coded this, so I don't know if it will TLE or not. It really depends on your implementation. So if you guys want, you can try coding it like this. But you actually won't be able to do it for like, oh, you guys won't be able to do the same thing for like this question. The one I've given you guys for homework actually. This one, this technique won't work. You will need to do what I'm gonna explain now. Or there's another technique, which I'm not gonna cover because it's a very weird technique. But you'll pretty much have to do what I'm doing now. So I don't think anyone here will actually be able to guess what the technique is because this is a very specific technique that only applies to sliding window. Also, by the way, another n log n solution would, so this is n log n and not n log w, or n log m, where m is the max size. So it would just be segment tree because that's pretty trivial, right? Yeah, you can just do a segment tree. So the original solution I said is n log w. The reason it's not O of n is because it doesn't take constant time to remove an element anymore. It takes O of the number of bits. So you know what? Instead of w, I'll call it b, if that's a bit easier. It takes b time, where b is equal to log 2 of the max value. It takes this much time to remove and add an element. It takes this much time. Don't you need O of log n to calculate the OR? No, it is again going to be O of b to calculate the OR as well, if you're iterating over bits. Now, if you do it with a segment tree, then you're going to reduce this to O of n log n, which may or may not be better. I think in this case, maybe it will be worse, or maybe if you have an iterative sec tree, it will actually pass. But anyway, I mean, there's a better solution. And now that I've discussed all of the worst solutions, I think it's about time to discuss the better solution. You know, I'm actually not even going to, or I am going to explain it, but for explaining it, what I'm going to do is I'm going to draw an array. Okay, I'm going to say k is equal to 3, okay, as an example. And I'm just going to draw an array. Yeah, this is fine. Okay, what I'm going to do, I'm going to take a different color, and for every single prefix I'm going to compute something like this. Okay, for every single prefix I'm going to compute something like this. I'm going to reset it over here. I'm going to start again from scratch. I'm again going to do this, and over here is just going to be 1. Actually, I will add one more element to the end. Yeah. Yep. Okay, so I'm going to compute this for every single prefix. Okay, now I'm going to take a different color. I'm going to compute something pretty similar for every single suffix. Now I'm just gonna wait for like I'm gonna wait for, let's say, like 2 minutes, and I'm gonna see if anyone can figure out, using this, what a solution, what a possible solution can be. Yeah. I'm not gonna say anything for now. I'm just going to put this on screen. Yeah, I mean prefix OR. Yes, I mean prefix OR. The range over here represents that I've taken the OR of all of these elements. Or just actually you don't even need to know what OR does. This will apply for any operation. It's not dependent on OR actually. But basically what OR does is if any one bit is on, then the bit is on in the result. Or if both of them are on, then also it is on in the result. So it's like at least one should be on. Anyone with a solution? Yeah, it's basically that. But it's like for every single bit. You can OR the green lines and manually OR the rest. Hmm. Hmm. I don't think that would work. I think it would be like, what if K is very big, right? That's the issue. Oh wait, but you're saying you choose K that is specific. Even then it would be like n root n or something. And that's strictly worse than log, right? Hmm. Yeah, sure, I'll give you guys time to think. Motivation? Uh, you guys can do it. I believe in you. Oh, but then, oh, you want hints? You want hints? I mean, this diagram itself is a very, very big hint. Like, this diagram, insanely big hint. Size is irrelevant, big hint, small hint. I don't know, man. I mean, if I give a big hint, it would be pretty obvious what the solution is, not going to lie. And maybe with a small hint, it wouldn't be that obvious. By the way, this is the last problem I'm going to cover today. After this problem, the lecture is going to end. So, you know, you can give your all in thinking about this one final problem, and after that, we'll be done. I mean, I'll be done. You guys have to do the homework problems, which are actually pretty interesting. There's one in the sliding window section that, like I said, the min one can be solved with the same technique. Actually, you can use the same technique for I think like all of them, or not all, but a lot of them. I think it's pretty reasonable to realize that. I mean, think it's pretty reasonable to be able to finish the homework in, I don't know, like maybe 3 days. That's a pretty reasonable time. Uh, each range can be represented or of some green lines. Like, how would you do it for like, how would you do it for like this range? Let me actually draw a range, because that I don't think that's correct. The thing is, how would you do it for this range? Also, why is this color so weird? Wait, I want some better color. And also, how do I make my size a bit bigger? Yeah, okay. Yeah. Yeah, this is a bit better. Let's take this range. Uh, let's see. For I equals 2 and j equals 4, we can or the green line and the blue line with, yeah, this is actually correct. This is actually correct, yeah. So the key thing was to realize that you can always take a green line and a blue line. If that's what you meant, okay, then you were correct. If that's what you meant, then you were correct, yeah. You can always take a green line and a blue line, and you can OR them together, and you get the result. So, for example, let's do it for this range over here. For this range, what two things are we going to take? Well, we're going to take this. Okay, wait, my pen size is still big. I need to make it small again. Not that small. Take 2 pixels, yeah. So we're going to take this thing, and we're going to OR it with this thing, right? Let's actually take one more range. just to show exactly what's going on. Uh, let's take the next range only. So this is going to be 2, this is going to be 4. So what are we going to take over here? We are going to take this, this. We're going to OR it with this. That's going to give us this range. So in fact, I don't want to spoil this part for you guys, so we're going to go back here and we're going to see what we did. We took this and we ORed it with this. So can you guys tell me that okay, I don't know if I should, I don't know if I should tell you because I guess you guys are tired, or if I should let you guys figure it out by yourselves. I'm not sure what the best strategy would be. So I want you to figure out like a formula, like I showed you the ranges visually, right? I want you to figure out which two ranges exactly it is. Be suffix till an I percentage or the prefix till k gets completed. I'm not too sure. I didn't I mod k if it is 0. Oh yeah, that's correct, yeah, but I want like the final formula, like so one more convention I should say is that prefix of I is equal to like like over here where it is starting, where the line is starting to extend from, that is where my thing is. So prefix of 0 is this line over here, prefix of 1 is this line over here, prefix of 2 is this third line over here. Okay, that's what I'm saying. And then suffix of 1 is the three things over here. Sorry, suffix of 0 is the three things over here, suffix of 1 is the thing I've drawn the red arrow at, and suffix of 2 is just this one element over here. If it's I mod k equals 0, we include the prefix green till this, green, blue till that. Well, it's actually, so suppose we wanted to do L to R. Suppose we wanted to do L to R. The answer is this, which is actually pretty nice. I mean, I thought the red arrows would have given it away, but I guess not, but that's okay. Like, you can see the red arrows correspond to the start and end of the range exactly, right? It's literally that easy. I kind of feel bad for spoiling it, this is a very nice thing to see yourself, but I mean, it's okay because, but yeah, it's very nice, I know. Uh, so, but I didn't want to spoil it, that's the thing. But it's okay. Yeah. So that is the solution to this problem. I would show you my implementation. Okay, I mean, how many people here want to see my implementation? Okay. So majority want to see, I guess. So I guess I'll have to show. Uh, I'm going to put it in the blog as well, but I still feel like I should show it if people want to see it. So this is actually it. It's like 30 lines around. And as I promised, the last part is just this. I and I plus k minus 1. Because that's the L and R in this case. It is very, very nice. So I will share this. Tell the other way. What is the other way? Like you mean the n log n way? Oh no, this is the only OFN way. There's no other OFN way. This is the OFN way. No, I don't think so. I don't think there's any other sliding window way. Over here, we are heavily relying on the fact that firstly that it's static, and we know all of it from before, and secondly that we're only gonna have a window of size exactly k. I mean, it's like limited, but it's still pretty powerful because it's a very nice. I mean, I feel like sliding window of same size will still somehow like show up in these kind of problems. It can sometimes show up, so it's actually a pretty nice technique to know, and it's a very magical technique as well. Okay. Yeah, so anyway, I think I've covered everything I want to cover. I'm going to post a problem set with around 11, I think 10 problems, some of which I have covered in this lecture itself. Like I want, like the problems will like include this, and some of which I just want you guys to do for homework, which are almost the same principles as what I have covered. It will use exactly what we have covered basically. So yeah, I hope you guys like the lecture. Hope you guys learn new stuff. That's it from me. Yeah, cool. Thanks for attending, guys. I mean, that really depends on the others, unfortunately. Yeah, I mean, you guys get so many free CSES solves from this. I feel like that's the best part, right? So many boosted problems. You know, now it's like now you can just speed solve them. Best part of attending. Actually, I feel like this is not that unreasonable. Not all of them. I think some of them you can't combine that trivially, but for the ones that have an operator plus and O1 defined, you can use this exact same technique to just like insta solve all of them. So it's like kind of a jack of all trades technique. Okay, but I hope you understood the DSU. I hope at the end it made sense. Because small to large is kind of hard to grasp. Uh, and even if you didn't like fully understand it, hey, I mean, like you saw the AC and you saw how the previous thing failed, so I mean that will definitely convince you that it's useful. But yeah, anyway, bye guys.